Welcome everyone to the 5th anniversary of the Halıcıoğlu Data Science Institute. We have quite a big program ahead of you, an exciting program, and we are going to start just a little bit early just to make sure we stay on time. So without further ado, I'd like to invite Dr. Continetti, Senior Associate Vice Chancellor, Dean Designee of the HDSI, and he'll introduce the proceedings.
Well, welcome everybody. It's a great pleasure to welcome you here today to the 5th anniversary celebration of the Halıcıoğlu Data Science Institute. I am Bob Continetti, Senior Associate Vice Chancellor for Academic Affairs, but today I'm speaking to you in my role as Dean Designee, supporting Director Gupta and the HDSI community in building this unique academic unit. And it is an academic unit like no other at UC San Diego, although as I'll mention in a minute or two, we hope to transition it into one that's more like others in some ways. But at the outset, let me start by thanking our benefactor, Taner Halıcıoğlu, and the Halıcıoğlu family for the vision and opportunity to make this institute a reality. And also let me thank Director Gupta, his leadership team, and the faculty, staff, and students who have made HDSI the success it is today, a day where we see it moving into its permanent home on the UC San Diego campus. It's really been an interesting journey to get here over the last 5 years, and even in this year, a number of important milestones were passed as the Institute has grown. We launched our graduate programs, the PhD program, the master's program, as well as the first online master's degree at UC San Diego, the online master's in data science. We appointed the first 3 HDSI endowed chairs. And noting that we're here today, again, in the newly renovated data science building, we finally have a common home for HDSI. And this is a physical reality that is going to provide a real boost, I think, to our sense of community and developing the momentum to move this institute forward in the coming years. So as Dean Designee, I've been working with Rajesh and supporting HDSI since its inception. And one of the most exciting things I've found about the novel structure is that it really is a true transdisciplinary academic organization that's perfectly poised to make fundamental contributions to the broad field of data science. We're seeing the impact of data science all around us today, from how we interact in society to the discovery of new patterns and processes in the universe, as well as the ethical foundations that are required to employ data science responsibly. Even in just the last year, of course, we've seen a broader recognition in society of the questions at hand with the explosion in public awareness of the promise and challenges associated with artificial intelligence. Well, one thing I know is in dealing with these new realities and new questions is that the environment here at UC San Diego is the perfect laboratory, as it were, for making a data science institute like this successful. Interdisciplinary has been a long tradition at our university since its very beginning. The university began at the Scripps Institution of Oceanography near the beginning of the last century, and if anything is a interdisciplinary unit, it's the Scripps Institution of Oceanography. It brings together people all across all disciplines to study that common problem. Now today, we look at UC San Diego, 63 years since its founding, with this incredible general campus, incredible health sciences campus, as well as Scripps Institution of Oceanography. We have here a place that, I would say is becoming second to none, especially as a public university. And this is really an incredible environment for the innovation that paves the way for new institutes like the Halıcıoğlu Data Science Institute. And I think what we're going to hear about today is that innovating is what HDSI is doing, developing educational and research programs that harness the power and prospects of data science for the future. With the leadership of Director Rajesh Gupta, the support of the faculty, and the academic leadership of the Executive Vice Chancellor and the Chancellor, we've made incredible progress over the last 5 years. An intellectual core has been established among the faculty, including some of those who joined who are already here at UC San Diego, as well as the faculty we've appointed directly into the Institute. And we've built the infrastructure to support one of the largest undergraduate data science programs in the country, one that includes a challenging capstone project that puts the icing on the cake, as it were. These capstone projects that students have engaged in are incredible and span a wide range of problems and applications. Beyond our new graduate programs as well, further innovation is being pursued, including a novel MD/MS program that will help provide medical doctors of tomorrow with the data science knowledge that is becoming increasingly central to modern medical practice and research. Finally, as we continue to grow, we look for further opportunities to build our strength in data science. And in this regard, I'm most excited about the prospects for establishing a new school of computing, information, and data sciences. This will bring HDSI and the San Diego Supercomputer Center together in a new transdisciplinary school that will leverage our resources in data science and applied data science, powered by state-of-the-art computing hardware, to ensure that UC San Diego is going to have an enduring impact in this field throughout the rest of this century. So I believe the future of the Halıcıoğlu Data Science Institute at UC San Diego is bright, and it has been an honor, personal honor, to support building the effort that's going to have a lasting contribution to our society. So turning back to today's celebratory event, we're going to be celebrating the accomplishments of the Institute's first 5 years, bringing researchers, academics, and colleagues from industry together for a showcase of talks and panels. I'm pleased to welcome you all here today, and I want to have special thanks to our keynote speakers, Professor Peter Bartlett from UC Berkeley and Professor Eric Topol from the Scripps Research Institute. And in addition, I would like to thank again your director, Rajesh Gupta. His relentless enthusiasm and hard work have played a key role in setting the stage for today. I've known Rajesh now for almost 15 years, and he continues to impress me on a routine basis. And it was not a surprise at all for me to learn the other day that Rajesh had received an Excellence in Stewardship Award based on his contributions to building the quality programs here that have brought together alumni, faculty, donors, and local community members to build HDSI as an enduring institution. With that, then, I turn this over to the director of the Halıcıoğlu Data Science Institute, distinguished Professor Rajesh Gupta.
Thank you, Bob. Five years. For some strange reason, I feel pretty much the same way I did 5 years ago in the HDSI auditorium. A sense of excitement, something new is going to happen. But 5 years have passed. We are in a new building. We are in the sign. This actually means something. When I put my hands on it, it actually means people. It means programs. But for some reason, there's a sense of excitement, but there's a sense of apprehension also. We'll be able to rise, we'll be able to do what we are promising all this. We have a program and we have a community. But somehow, you always look at the miles ahead, not the ones behind you. Believe it or not, I used to do half marathons, never did full. And it was like the mile 6 or 7, you're thinking, we made it halfway. And you're looking at the next mile, you're not looking at the one behind you. And when I look at the next miles, we have an exciting new school coming up. Here in this quad, Warren Mollis Wall quad, we have a number of engineering schools. Mechanical engineering, next is computer science. When you enter the Walton Mall, is flanked by computer science and data science. That's the vision that is emerging. How well will this vision perform, especially with another school? We have Arvind and Joanne Jacobs School of Engineering. Arvind is here, thank you for coming. And the two together will put UCSD on a map. HDSI was always about people. That is why we spent first 5 years not worrying about space. When I was asked, where is your building? I said, we have no building. And there were 5 or 6 different places which put up our sign there. They wanted us to be part of them. One of them was San Diego Supercomputer Center, an extraordinarily warm host. Frank Werthwein, director Frank Werthwein is here, and right there. And we couldn't believe how accommodating they were. There were people who were in their offices for 20 plus years. We didn't ask them, but they somehow volunteered to move to another location to make room for us. And we grew. We took over one floor, then we took over another floor. And, well, not took over, but occupied. And now we are at the verge of a final proposal. Pre-proposal has already been approved, of a school that will bring HDSC and HDSI together. We could not have imagined that 5 years ago. And if we did, it would be considered land grab or territorial grab. But it wasn't about that. It was about people working together. And it will be the same going forward. Whether you're in a school of engineering or you're in a new school of computing information data science, you'll be working together with people, maybe in Franklin Antonio Hall, maybe in this HDSI building, maybe in computer science building, maybe in mechanical engineering. We have engagements with them as well. And we created a program in which I'm proud to say every student is mentored by a faculty member, by a teacher, not for 1 quarter, but for most of the year. I wanted it for whole 3 quarters, but some students graduate faster, so we had to do it for 2 quarters. And in that year, they're only doing electives and they're only doing capstones, because that becomes their portfolio, that becomes their identity. And when they go out and they succeed in their corporations, they give me, HDSI, UCSD, its identity. Now, all of that happened. I happen to be the face of it for getting the biggest cheerleader, but a number of people supported us and made this happen. So I'm going to take a minute, and this is one of the very few times I take written list for my talks. I want to make sure that I acknowledge. Firstly, I'm like a foot soldier in an academic administration who was empowered by the leadership, the chancellor, the executive vice chancellor, the senior associate vice chancellor, to be part of the strategy, to be part of one devising the strategy. That's an enormous honor. Generally, people like me are given a task and say, go do it. And in this case, we did the task, and the leadership made this possible. My own department, computer science, and its dean, Al Pisano from engineering, have been extraordinarily generous. For the last 5 years, I have spent all my time building HDSI as a faculty member of computer science. I'm teaching this quarter, but really, I don't have to. They were generous with volunteering me to do a new thing. My biggest thanks to them as well. There were 187 founding faculty. There was a list of 186, and 187th was me. So oftentimes I didn't count myself, so it's 187. These are the blue badges you see across the campus on the doors. These founding faculty didn't just volunteer their name. Before this community arrived, these were the group of people who talked about what data science meant. They wrote about what data science meant. They created clusters of areas where data science will be impactful. And it was all across campus. My most sincere thanks to them. This leadership, this faculty together, Thank you for trusting me with that responsibility. This journey had many fellow travelers. Before there was HDSI, we created data science undergraduate program. And that was a program with a number of faculty members drawn. One of them was Jeff Remmel. He passed away before HDSI could come into existence, but just before that, he defined the data science program. And then, of course, my founding co-partner, Jeff Allman, our team of associate directors, Ginny Disa, Dimitris Politis here, our faculty fellows, Brad Wojtek, Ilkay Altintas, Arun Kumar, and Tara Javidi. Our industry fellows, the leaders of our graduate undergraduate program, Yusu Wang leads our graduate program, Justin Elries leads our undergraduate program. All of that effort has come together to make HDSI what it is today. We were very pleased to put 3 endowed chairs, the beginning 3 endowed chairs, to our strongest champion and our biggest hard workers. You saw Vineet Bafna, he curated this program, and the ones before that. Vineet has been helping us build our biomedical and biodata sciences faculty, a group of faculty together as a core area of UC San Diego. Dimitris Politis, Ginny Disa, they are our inaugural chairholders. The Senate was very particular about making sure we followed all the rules, and we said there will be no exceptions to anything we do. There will be exceptional results that will come out, but the faculty governance is a key part of it. So there's a biggest chicken and egg problem. How do you hire faculty when you don't have faculty? Because faculty hiring and academic programs is solely a responsibility of faculty, not administration, especially in the UC system. So there were 16 faculty members who were the founding faculty, I'll take their names, who stepped forward. 7 of them actually transferred quarter of their time to SDSI to teach courses in SDSI. They were the ones interviewing, voting on faculty candidates to make sure that we are able to build the group. And now we have recruited 28 faculty, 11 of them jointly with other schools. So the founding faculty were Alex Cloninger, Armin Schwartzman. I'm happy to see many of them here. Arun Kumar, Brad Wojtek, I know he's on a sabbatical. Dimitris Politis, Ari Arias Castro, Frank Werthwein, thank you, Frank. Ilkay Altintas, Yelena Bradic, Julian McCauley, Rayan Saab, Rob Knight, Shankar Subramaniam, Tara Javidi, Ginny Disa, and Yoav Freund. In the process, we created over 24 committees, recruiting committees, drawn from faculty from across the campus. And it will not be an exaggeration to say we probably conducted more than a few hundred interviews. Just last recruiting season, we had 1,400 applicants for our faculty position, out of which we have now 2 accepts. But all of this machinery of academics has another machinery underneath it that works quietly but efficiently. And that machinery is a group of staff members led by Jen Morgan and Kyle Hofer-Mora. I was so happy to see Kelly O'Mary. Kelly is running around here for this program. Come back to SDSI. She was our employee number 1. She remains our employee number 1. Logan Wiedenhofer, who manages pretty much all activities associated around me. And this group of people has put together an event planning committee that really, this building, up until yesterday, they were still laying out the tiles on the backyard. So please be gentle. And the bathroom, when you turn the faucet on, that's probably the first drop of water they're seeing. Vineet and Ginny, Simeng, Zheng. Simeng probably has been working non-stop for last 3-4 days, so amazing. Thank you, our event manager. Jen Morgan, Eric Mion, Logan, Christina, and Matt Scott. Matt is our building maintenance and facilities maintenance czar. I would be remiss to not thank our Senate leadership, starting from Bob Horowitz to today, John Hildebrand, and every Senate chair in between. We had quarterly or at least annual reviews with each of them, of the Senate chairs, to make sure we were on track. Then lastly, there's a group of people who is very special to me, and this group of people have been a source of encouragement and a source of counsel, advice, since its founding, and that's our advisory board. They're not as publicly seen, at least with it as HDSI, but starting with Arvind Jacobs. Arvind, thank you for volunteering your time. I see Eugene Ishkevetsky. Thank you, Eugene. Sanjay Jha, DJ Patil, Marty Cooper, and Arlene Harris. They have been a source of at least giving me confidence that things will be all right. And they have built organizations, so this is something that we can do. There are a lot of people I would like to thank, but my most sincere thanks are to people who have enabled me to pursue the dream in the first place. The leadership of UCSD volunteers my time, volunteers me to get there then. Tanir Halıcıoğlu, who I count among my friends, and Halıcıoğlu family have been the greatest champion, and rightfully so, Halıcıoğlu Data Science Institute. Tanir is a graduate of a computer science and engineering department at UC San Diego, and he has been very generous with his time. In fact, the first engagement Tanir did with us and continues today is actually teaching a class on DevOps. Now, majority of the faculty don't know what DevOps means, which means our students go out knowing something that they would have never known in any other school, and it's enormously practical. Tanir takes time to meet our tutors, to meet our instructors, to spend time with them, to listen to them as to what their career plans are, give them advice. And Tanir is now at the center of creating an ecosystem for data science in San Diego area. In addition to HDSI as an academic unit, he is also founder of the Data Science Alliance, which in my book, I call it constant keeper of AI for future. So without much ado, I would like to invite Tanir to say a few words. Thank you, Tanir.
I'll keep it quick because I think I know we're short on time. First of all, thanks everybody for being here. This is pretty impressive, and as Rajesh alluded to, it seems like it's 5 years, but is it 5 years? And I know we had COVID in the middle there, but you know, I fundamentally am just extremely impressed and humbled by all that's been achieved. Rajesh, this could not have been done with anybody else other than you. Like, you are a driving force. So again, I'm gonna keep it short and sweet. Again, thanks everybody for being here. I'm really excited to see what the future holds, especially with things like the skids coming up and having even more collaboration between units here on school. So thanks.
Since our founding in 2018, the Halıcıoğlu Data Science Institute has been an academic force of nature, rapidly advancing the field of data science at UC San Diego and the global society at large. We're an institute established from a vision to unlock the power of data for the better humanity. In the past 5 years, we've pushed the boundaries of what's possible. Join us as we take a journey through our landmark achievements in the past 5 years. We've welcomed over 4,800 students annually into our data science courses and graduated our first cohort of data science undergrads in 2021. We launched our Masters of Science in Data Science, an online master's and a doctoral program, expanded our research and teaching expertise by appointing 47 faculty, which includes 7 new recruits in the past year, honored our first HDSI Chancellor's Endowed Chairs, who are renowned scholars and recognized innovative leaders in their field, Virginia Desa, Dimitris Politis, Vineet Bafna. Hosted over 200 events as part of our lecture and outreach, sponsorship, and special seminar series. Awarded 84 scholarships to undergraduate researchers. Bolstered our research abilities with visiting scholars and over 15 postdocs. Gained new industry partners who have enriched our student experience through mentorship and research opportunities to work on real-world datasets. Sent off 504 data science graduates who have gone on to use their new skills and knowledge to lead data-driven innovation in some of the most prominent organizations in the nation. One of our most recent achievements, welcoming our first incoming class of master's and PhD students. As we embark on another year, we're excited to welcome another first. The Halıcıoğlu Data Science Building, a dedicated space that marks our presence, where collaboration and innovation will thrive. We're proud of our successes, but we know this is only the beginning. As HDSI grows and progresses onward, we'll continue cultivating a culture of academic excellence and innovation, pushing beyond the limits and making a positive impact on the world through the power of data. Success is just the start.
I'd like to introduce our keynote speaker today, Professor Peter Bartlett. He's a professor in the Electrical Engineering and Computer Science Department and in the Department of Statistics at UC Berkeley. He's also the director of the Foundations of Data Science Institute, head of Google Research Australia, among many other affiliations. Professor Bartlett is an international authority in machine learning. He serves as the associate editor for many journals in the field and has co-chaired the top conferences, including NeurIPS and COLD. Professor Bartlett has won a number of awards for his research. These include the Malcolm McIntosh Award Prize for Physical Sciences. He's the Medallion Lecturer of the Institute of Medical Statistics, a Fellow of the IMS, and a Fellow of the ACM, among many other awards. So let's welcome Professor Bartlett.
All right, thanks very much, Vineet. Let's see what we have here. All right, so thank you very much for having me, for the invitation. I'm delighted and honored to be here. Congratulations on this milestone. This is really fantastic. My talk today is joint work with a bunch of collaborators. So let me acknowledge them first. Niladri is at Stanford. Spencer is about to start at UC Davis. He's a postdoc at Berkeley. Wei is at University of Michigan. Phil is at Google. Gabor at Pompeu Fabra. Nati at TTI Chicago. Alex is in statistics at Berkeley, and Gal is in Hebrew University. So actually, let me take this chance to say congratulations. I've been a enthusiastic supporter of the Halıcıoğlu Data Science Institute for the last 5 years. Yeah, how's that? Better? All right, thank you. And actually that 5 years coincided with the 5 years that I was the Associate Director of the Simons Institute for the Theory of Computing. And, it's been great to see the collaborations and connections between those two institutes. We've had a whole lot of researchers come and visit for long-term visits as in our collaborative research programs, at the Simons Institute, and we've had a formal partnership collaborating on recruiting junior researchers to our programs. So fantastic to see HDSI grow as it has, and looking forward to the next 5 years and so on. So congratulations again. All right, so my talk today is about the science of deep learning. You know, we've heard all about the huge impact that AI is having and is poised to have. And of course, AI means deep learning these days. But when you talk about data science, when you talk about the science of deep learning, there's really a lot that we don't understand. There are lots of aspects of this data science technology that are really rather mysterious. And of course, you know, these tools have shortcomings and limitations that we'd really like to address. So when we're designing a prediction method, such as a deep learning approach, there are three key issues that we're concerned about, and concerned about trade-offs between those issues. There's the approximation question of, you know, what's the family of prediction rules that I'm working with, and how good is that, is the best in that family. There's the optimization question of taking training data and producing a good prediction rule. And there's the estimation question, the generalization question. So we have a good fit to training data. Will that also lead to accurate predictions on subsequent data when it's out there and deployed? And in classical settings, you know, we have grown accustomed to certain approaches to addressing these issues. So in the approximation question, we're used to working with rich non-parametric classes, but keeping careful control of the complexity of those classes. The optimization question, we're used to formulating our problems as convex optimization problems, because we have guarantees then about being able to efficiently find good solutions to those optimization problems. And for the statistical question, you know, we're often concerned with uniform convergence sorts of results, being able to say that uniformly across the class of prediction rules that we're working with, doing well on a finite training sample implies we're doing well on subsequent examples, because expectations and sample averages are close uniformly across across that class. That's what we're used to, but in many ways, deep learning methodology is very different. For the approximation question, you know, this notion of depth or compositionality seems to be important. That's maybe not so at odds with our classical approaches. On the optimization side, on the other hand, you know, deep learning methods work with these crazy non-convex optimization problems and use really simple first-order gradient methods to optimize these, to solve these ugly non-convex problems, and somehow they can efficiently find good solutions. Over-parameterization seems to be the key here. Having far more variables than constraints in the problem seems to be really important. But you know, that's rather striking. The other striking thing in the generalization direction is that these solutions that practitioners find to these optimization problems are actually too good to be true. We're finding solutions that fit the data better than we should expect, and yet they're still predicting accurately. So they're certainly overfitting, but that overfitting is benign, and that's the phenomenon that I want to focus on in the talk today. Okay, so let's go back to undergraduate statistics, a simple prediction problem, and you know, what statistical wisdom that we've been teaching our undergraduates has to say about complexity versus fit to the training data. So let's take a bit of a cartoon example. We have some covariates, and we have a response variable that we'd like to predict with those covariates, and perhaps we're fitting a linear relationship between those covariates and our response variable. So we go out and gather some data, like these blue points, and we come up with a linear fit to the data, like this line. And, with this data set, maybe we've got a pretty good estimate of the conditional expectation of that response variable given the covariates that we have. Of course, things might be very different if we had a smaller data set. All right, so these two, I don't know if you can see that, but there are two red points here. If that was our data set and we fit a linear relationship to just that data, we'd have a terrible prediction of the response. And of course, the issue is that somehow we didn't have enough data for the complexity of prediction rule that we're working with here. In the simple linear case, we can think of complexity just in terms of number of parameters. But if we come up with a nonlinear prediction rule, there's certainly a notion of complexity where this fit is too good to be true. We have something that's too complex for the data that we have, and we shouldn't expect to be predicting accurately in this case. So that's the conventional wisdom. But it turns out that deep neural networks practitioners have shown us that they can be trained to zero training error for a regression loss and still give good predictive accuracy. These two graphs are from an experiment that a group at Google did a few years ago now. On the x-axis of both graphs, there's the amount of noise in the problem. So we're guaranteed of having some level of noise in these problems because it's been added. On the left is the original data, and as we move across to the right, that data is corrupted more and more with noise in the labels. The top graph is showing how long it takes to get to a perfect fit on the training data. The different lines are different neural net architectures. And the bottom graph is showing the performance on independent test data. And we're seeing that even though there's noise in the problem, even though we're getting a perfect fit to this noisy training data, we're still getting a graceful degradation of the prediction accuracy. We're still getting good predictive performance. Misha and others have shown that this arises not just in the deep learning setting, in other settings also. It's really striking here that there's none of this classical trade-off between the fit to the training data and the complexity of the prediction rule that we're seeing. It's certainly overfitting. We know that getting a perfect fit when there's noise in the problem is better than we should expect, but that overfitting is benign. The predictive accuracy is still rather good. So as I say, we don't have this usual trade-off between the fit to the training data, maybe the average of the squared error on a training sample, and the complexity of the prediction rule, whether we think of that in terms of the number of parameters, or the scale of our prediction rule, or the smoothness of our prediction rule, and so on. Okay, so it turns this statistical wisdom on its head. This is a picture of my bookshelf. I was thinking actually probably Yoav, your books up in there somewhere. But in all of these, in teaching our undergraduates, we've been telling them forever that finding an interpolating fit is a bad idea. You can find these quotes from various places. A function that interpolates the data is not a reasonable estimate, and yet here we are in the deep learning setting of doing exactly that. So this is really striking. It's really a new statistical phenomenon. We're getting good prediction when we have a very small training error for regression loss, even though we know that the data has noise in it. This is really defying the statistical wisdom that, as I say, we teach our undergraduates. Okay, so this arose actually in one of the collaborative research programs at the Simons Institute, just around the time that HDSI was getting started, and there was a group of us that got talking about this particular graph in the talk of that paper that I mentioned from that group who were at Google at the time. So Misha Belkin was one of those. Actually, a whole lot of San Diego connections, right? It was Misha, Matus Telgarsky, and Daniel Daniel, Sue, all got talking about this phenomenon. And I'll say a little bit about some of Misha's early results in this direction in a moment, but there was, very quickly a whole lot of work in this direction trying to understand this, really new phenomenon. And then a couple of years ago, there are these review papers. Misha had one, and I had one with Andrea Montanari and Sasha Rachlin. They came out in Acta Numerica. And I want to convey the intuition that we gave in our paper for this phenomenon, for the kinds of cases that we understand here. So just to give a quick overview of that, situations where we know how this benign overfitting phenomenon occurs are cases where our prediction rule decomposes into two pieces. So there's a simple piece that's simple in a classical sense. The complexity of that piece of the prediction rule is low, and we're not breaking any rules there. And then there's this other component. You can think of it as a spiky component. It's a piece that is good for fitting perfectly to the data, but it plays no role in prediction. It doesn't help. It doesn't hurt. So as I say, classical statistical learning theory applies to the simple piece, and the other piece is something new that's plays no role in prediction. Okay, so let me start with a very nice example, and this was the first example I think that that exhibited this property, and this is work of Misha Belkin and collaborators. So it's Nutter-Raya-Watson kernel smoothing. So here we have a sequence of XY pairs, X1, Y1 through Xn, Yn. The Yi's are real values we want to predict. And we make that prediction for a new point with this rule F hat, which is a convex combination of the Yi's. And the weights in that convex combination are given by some function of how similar the X is to the various Xi's, right? And we use this kernel K sub H to give us those convex coefficients. If X is very close to an Xi, then K sub H should give us, a nice big weight. If it's far, then the corresponding Yi plays very little role in the prediction. Okay, this is very classical. And typically we think of these kernels as nice, well-behaved functions. But if we look at this sort of singular kernel, so it's compact, something like an indicator of a region around the Xi, but then there's this big spike at 0, right? So the value of this kernel goes off to infinity at 0. Then it turned out, Misha and collaborators showed that you could actually get optimal rates for appropriate smoothness classes with a suitable choice of the width of these kernels, the bandwidth parameter. You could still get optimal rates. But if you think about it, when the kernel goes to infinity at 0, then when this point X passes through one of the points in the sample, this Xi, you're getting an infinite value of the kernel means the weight is going to 1 at that point, so you're interpolating perfectly. You're getting a perfect fit on the training sample, but it turns out getting minimax rates. And the point, and I guess, okay, here's an illustration of what's going on there, that the spikes there have very small weight. So even though you're interpolating the data, you're not having too much of an impact on the predictive accuracy in an L2 sense. And just to relate that to this intuition, we can think about splitting up that prediction rule, that kernel smoothing rule, into the simple component that's something like the regular compact kernels that we're used to, together with that spiky piece in the middle that has a very small norm in L2P. So it doesn't play a significant role in the prediction. Okay, so here's the agenda for the rest of the talk. I want to tell you a little bit about some results in linear regression, about the relationship between benign overfitting and sensitivity to adversarial perturbations, a certain robustness property, of prediction rules. I then want to talk about some of the related cases with neural networks. They're two-layer ReLU networks looking at classification problems where we see a similar phenomenon. Okay, so let's start with this very classical question of the problem of linear regression. So this is perhaps one of the simplest prediction problems we might consider. We've got covariates X in some inevitably high dimensional space. So think of D here as big, and a real valued response variable. We're interested in linear prediction, so we take an inner product between our covariate vector and a parameter vector. And we're making the assumption that the truth is linear, that there's some theta star that gives us that corresponds to the true parameters, the true linear relationship between X and Y, together with some zero mean independent noise. Okay, and we make some assumptions about the noise distribution and about the X distribution, so that the tails are nicely behaved, so that we have some don't have too much concentration, but we have nice concentration. I'll sweep that under the rug. And under these assumptions, we want to consider this benign overfitting phenomenon. Okay, so we want to think about cases where we're getting a perfect fit to the data. In the linear case, that means we're in very high dimensions, right? We have to be in a dimension with random x's. We have to be in a dimension that's big enough to fit everything perfectly. That means the dimension is larger than the sample size. And so, we're going to be thinking of cases where there are many of these linear prediction rules that will fit the data perfectly. And so which one do we consider? Well, motivated by this phenomenon of deep learning, this setting of deep learning where this phenomenon was observed, we think about gradient methods, simple gradient methods that optimize an empirical criterion. So if we think about gradient flow, so take our parameter vector and use a gradient method to optimize this L hat, the empirical risk, let's say squared error on the sample, right? The sum across the training sample of yi minus our linear prediction for the covariate vector xi, or squared. If we do gradient flow starting at 0, then we end up solving this optimization problem subject to the constraint that we get a perfect fit on the data. We want to return the minimum norm coefficient vector. Okay, that's the minimum norm interpolant. We can use the sort of standard linear regression notation here. We've got a matrix X whose rows are the covariate vectors, and a vector Y of the corresponding response variables. So this is our training data. And the optimization problem we're solving is minimize the norm of the parameter vector that gives the best fit to that training data. And in our case, in the high dimensional setting, perfect fit to the training data. Okay, so that's the estimator we're considering, and we want to understand when it will give a perfect fit that still predicts accurately, near optimally. Okay, so let me introduce 3 more pieces of notation here. The covariance of X, we've got a covariance matrix here that we're writing its spectral decomposition. So we're thinking of these lambda i's as the variance in different directions, and they're ordered. So our covariate vectors have covariance in the principal component direction variance, in the principal component direction of lambda 1, lambda 2 is the next highest variance direction, and so on. And turns out these are crucial properties in this benign overfitting phenomenon. Theta star I mentioned earlier is the truth, the best linear vector, and there's a certain noise level sigma squared. All right, so just keeping that notation in mind, the goal here is to have the expected squared error as close as possible to the best that we can do with a linear prediction rule. Okay, so we talk about that as the excess risk for our prediction rule with parameter vector theta hat. And, it turns out you can write that as a quadratic form, just a function of how far your estimated parameter vector theta hat is from the truth theta star. And of course, it depends on the covariance matrix. It depends in particular on these eigenvalues of the covariance matrix. They're the ones, the large eigenvalues are the ones that matter a lot. We better make a good estimate of, come up with a good estimate of our parameter vector in those directions corresponding to the highest variance of the x's. Okay, so that's the criterion of interest. And then here's the result. This is joint with Phil Long, Gabor Lugosi, and Alex Sigler. So we have one of these linear regression problems. There's a certain notion of effective dimension, and I'll say precisely what that means in a moment. This little rk is a effective rank of the covariance matrix once you eliminate the k highest variance directions. So what's going to happen here is in these k highest variance directions, that's where all the action is happening, and the other directions are just going to be useful for overfitting. All right, so k star here is the effective dimension in those other directions in the input space. And the result is the excess risk has these two components. There's a bias component and a variance component. The interesting phenomenon here is that we're fitting perfectly to the noise, and so we should expect the variance component to be really problematic. So let's focus on that and not pay too much attention to the bias component. That variance component has a k star over n term, which is a lot like what you'd see if you were just solving a linear regression problem in a k star dimensional setting, plus this other term, n over capital R k star. That's another notion of effective rank. I'll say a little about that in a moment. So, what we need is that the effective rank of the covariance in this orthogonal subspace is really large compared to the sample size. That's what's going to give good predictive accuracy, near optimal predictive accuracy. And it turns out that's the best you can do. You can't improve on that. There's a lower bound as well with some suitable independence that, for instance, is satisfied by Gaussian data. So, all of these terms, up to constant factors, all of these terms are necessary. And I won't pay too much attention to the bias term, as I say. All right, so what are these effective rank terms? Well, they're looking at, how many roughly equal variance directions there are in that input space. So, ignoring the first k highest variance directions, ignoring that low dimensional subspace and looking beyond it, there's an L1 norm of those eigenvalues divided by an L infinity norm. That's one notion of effective rank. And the other one is an L1 norm squared divided by an L2 norm squared. Okay, so, you can think of them as the effective rank of the covariance in the low variance subspace once we've eliminated k directions in the input space. Okay, and as I say, there are these upper and lower bounds. One thing I want to highlight is you can think of this k star as a kind of effective dimension, right? That's where all the action is happening. The variance term that we see, that we can attribute to that, this noise level times k star over n is exactly what we'd expect if we were solving a linear regression problem in a k star dimensional setting. And it turns out, the corresponding term of the bias term, it's as if we're ignoring what's happening in that other subspace. So we're really focusing on this low dimensional subspace and effectively predicting zero everywhere else, which is just this intuition again, right? The prediction rule that is overfitting in this linear setting but giving near optimal accuracy splits into a prediction component, which is in this heaviest, highest variance subspace, together with an overfitting component. So in that orthogonal subspace, we're in a very high dimensional setting, so we can fit perfectly to the data, but in that orthogonal subspace, it has no role in prediction when we're in this high effective rank setting. Okay, so that's what goes on in the linear regression setting. You know, the explanation for these this phenomenon arising there is that, you know, it's all about the mix of eigenvalues of the covariance matrix. They're determining both how the errors in our parameter estimates affect prediction accuracy and how the noise that's in the labels gets distributed in this parameter space, and it's the combination of those two that leads to these leads to the result that we saw. The intuition is that we're seeing the noise energy, when we're seeing the noise energy distributed across lots and lots of unimportant directions, then it's not going to be harmful for prediction accuracy, even though we're fitting to that noise perfectly. So it really is an overparameterization phenomenon. We need to have far more parameters than the sample size. We need to be in this high dimensional setting. So lots of small eigenvalues that are roughly equal, and we get this split into a simple component and a rich benign overfitting component. All right, so that's the linear regression setting. Yeah, let me just take a little detour and you know, beyond the science of it, you know, understanding this new phenomenon, what benefits should we get from that? Well, overparameterization, if you think about the cost of overparameterization in a setting like deep learning, you know, that's a huge cost of computation, a huge cost of energy, right? If the number of parameters is growing as with the sample size, it's at least as large as the sample size, then our computation's growing at least as the sample size squared. So if we're going out and gathering, you know, internet scale training samples, this is really a big expense that we might be able to avoid. You know, for the cases that we understand, overparameterization seems to be important just for the overfitting part, but not for the predictive accuracy. You know, the really crucial aspect of these prediction methods, which raises the prospect of being able to get by with a much better performing learning method. Okay, so I think that's exciting. The next thing I wanted to mention is this cost of benign overfitting in some sense, the sensitivity to adversarial perturbations. So this is a robustness issue that, again, has arisen in practice in deep learning. People have seen that you can take a well-trained classifier, in this case for a image recognition problem, take an image like that one on the left, the classifier, the deep network that classifies it gives a confident prediction that that's a picture of a panda, with some carefully crafted noise added at a very low level so that it becomes an imperceptible perturbation of the original image. The same classifier confidently predicts the wrong thing. In this case, it goes from saying it's a panda to saying it's a gibbon, which might not seem such a terrible thing to be concerned about, but of course, if the left-hand picture was a stop sign and the right-hand picture was a speed limit sign, and there are similar examples of this sort, then and you're really using these prediction rules in an automated driving system, then this is a much more serious issue. So let's think about the linear regression case. When that label noise appears in the parameter vector, as it must, because we're predicting every point in our training sample perfectly, then it turns out we have this very strong sensitivity to adversarially chosen perturbations in the input. So in the linear regression setting, this is sort of a trivial exercise. You can show that that there is a direction in input space where a perturbation of the input in that direction can change the output enormously, right? So if you're in the benign overfitting setting, so the excess risk is no more than some number alpha, something nice and small, you're performing well in this overfitting regime, then the change that you see with this unit perturbation scales like 1 over square root of alpha. So you have this huge sensitivity to a perturbation in that direction. And of course, we should expect that because we know that we've got a perfect fit to the training data, but that perfect fit has a small weight in L2P. So we must have, a big L infinity norm in our big L infinity norm of a perturbation that corresponds to a small L2P norm of perturbation. Yeah.
But if you have a weak predictor to begin with, then benign overfitting is really not there. I mean, you have 57.7%.
Oh, yeah. So that's not a prediction accuracy. This is
It's a confidence.
yeah, confidence, which is it's probably a misnomer. I probably shouldn't have written that as a percentage. So yeah, you can interpret this is a multi-class classification problem with a large number of classes, and it's encoded as a one hot encoding. And the 57.7% says that something close to 60% of the total weight of the outputs is concentrated on Panda, which with a very large multi-class classification problem, is a very confident prediction of a Panda. But I don't think you should attach a
I see. Okay.
meaning to that confidence.
So is there a big spread from 57? The next class.
Certainly a big gap. This is 57, almost 60% of the weight. The next closest is, can be no more than 40%.
Oh, I see.
But, I think it's an even bigger gap than that in this.
Okay.
In this example, yeah. So it's not like this is a classification accuracy, yeah. All right. So we see that that trade-off between benign overfitting and this robustness issue, and we'll see that again in the case of two-layer ReLU networks. Actually, let me go quickly through this. So that's the linear regression setting. What about neural networks? So in ReLU networks, we have some results for gradient descent with two-layer ReLU networks for a classification problem trained with logistic loss. The kind of challenges here are that we have to consider the optimization problem now. This is much more interesting. We have, with gradient descent, we have this non-convex learning dynamics of neural net training, as well as the benign overfitting phenomenon, right? Understanding how we can generalize with an interpolating prediction rule, in this case a classifier, when we have noisy data. So it's the optimization question that arises here as well as the generalization question, and turns out that overparameterization is crucial on the optimization side as well in this setting. So the specific case that I want to tell you about is that the data distribution is in some sense very simple. The truth here is a linear classifier. So we have two class conditional distributions, the pluses and the minuses, that are nicely separated. They have these nice, log concave isotropic sort of properties. So one centered at plus mu, one centered at minus mu, and then we throw in some noise. All right, so we've got a nice linear classifier that's well separated, and then we flip the labels of a constant fraction of the training data, and that's our distribution training examples. And we're considering 2-layer ReLU networks trained by gradient descent. I guess they're smooth ReLU networks. So we're thinking of that, you can write it out this way, we're thinking of that as just adjusting the first layer parameters. So the ones that appear in this nonlinear way and give us the non-convexity of our optimization problem. The specific optimization problem is a logistic criterion, so it's a classification problem. We minimize a log loss with our noisy data and use a gradient descent approach with a certain step size. And we're considering these leaky ReLUs that are smooth. So, you know, positive lower bound on their gradient and upper bound on their second derivative. Under a bunch of assumptions, we have to have enough data. We have nicely separated means before we add the noise. We have, we're in a high dimensional setting, so our data is roughly orthogonal. Dimension is large compared to the sample size. The noise is some constant proportion. And we have a large step size relative to the initialization. So we're really not in a linear setting. We're far from the NTK regime, the sort of regime where we can approximate things by a linearization. So, you know, this is really rather different from the linear setting. This is joint work with Spencer Frey and Niladri Chatterjee. So you can say that when we run gradient descent with a suitable step size, suitably large step size, we can get a perfect fit on the training data. So the logistic loss is near zero on our training sample, and yet we're getting a test error that's near the noise level eta here, right? And gets closer and closer to the noise level exponentially quickly as a function of the sample size and the dimension. So we're certainly overfitting, getting that training loss down to zero, but it's benign. The width of the network, the number of these nonlinearities, isn't playing a role here. You know, it's a result that's independent in some sense of the width, apart from a condition on the step size. And by any notion, you know, we've got this very high complexity prediction rule. The norm is going to infinity. We're in a high dimensional setting. The width can be much larger than 1, but we're still getting this, you know, near optimal prediction accuracy with essentially zero training loss. So very much the same phenomenon there. Okay, in the interest of time, I won't go into this. It turns out we can say a lot more about the particular interpolating classifier that we see. Turns out that you're getting something that is, the parameter matrix converges to something that just has rank 2. So we're actually seeing something that looks a lot like linear discriminant analysis in this setting. We get something that looks a lot like the difference between the sum of the inputs for the positive examples versus the sum of the inputs for the negative examples, minus the sum of the inputs for the negative examples, and that's the classifier that we converge to. Something very much like that, at least. Including in the middle, right? So we end up getting, I mean, okay, just to focus on the last line here, since I'm out of time, gradient flow leads to a classifier that has a parameter vector that looks like just the sum of the yi's times the xi's. Actually with some weighting for each example, but that weighting is close to uniform. So we're seeing something that looks just a lot like linear discriminant analysis in this setting, which, you know, is enough in this setting to ensure that you get a perfect fit to the training data, but you're predicting accurately. You know, and we have this sort of striking simplicity of the prediction rule. On the other hand, it comes at the expense of robustness. You know, we've got this benign overfitting phenomenon, but at the same time, we'll get really non-robust classifiers, even though robust classifiers exist in this setting. So we can find a small perturbation of an input to give a very big change in the a small perturbation to give a flip of the prediction. Okay, so just to sum up, you know, I think this is really a a fascinating new statistical phenomenon that the practice of deep learning has revealed, far from the classical regime of having a trade-off between the fit to the training data and the complexity of our prediction rule. And you know what I've told you about, we have gradient methods in these high dimensional settings for linear regression and for classification with, I skipped over that part, but also linear classifiers, but two-layer ReLU networks, where we're getting a global optimum, we're approaching a global optimum of the, on the training data. The implicit bias that's introduced by gradient descent leads to benign overfitting. It leads to this kind of simple component that's good for prediction, and a complex component that plays no role in prediction but lets us do the overfitting, at the cost of having this big sensitivity to adversarial perturbations. Okay, you know, I think most exciting next steps are looking at what happens in actual deep networks, you know, the area where this phenomenon was first observed, and you know, do we see the same split into a simple component and a complex component, an overfitting component. All right, let me acknowledge collaborators and a few pointers there. And I'll stop there. Thank you.
All right, let's have a couple of questions. Go ahead.
Oh, yeah. All right. Super interesting, really. In the linear regression case, if you can find these large eigenvalues and the coordinates of these first principal components, sounds like you could do principal components regression and eliminate all these. Why do you need all these spiking components that cause too much trouble?
That's right. Really good point. You could absolutely do that in the cases where benign overfitting is going to work. I guess you know, at a high level, I'm not advocating to take a linear regression problem and come up with a perfect fit and use that. Right? There are much more intelligent things you can do in a linear regression setting. Really, the point here is trying to understand this phenomenon, when it does occur and when it doesn't occur, and you know, what that might tell us about settings like deep learning, where we don't have the luxury of finding a good way of solving the optimization problem in a low dimensional setting as we do by doing, you know, PCA followed by this perfect fit. But you know, it is suggestive of approaches that might be useful in that setting, where we seem to get a big benefit on the optimization side from over-parameterizing, right? And you know, maybe there is an analogous approach in that setting where we can just as efficiently work with something that doesn't exploit the over-parameterization and doesn't have the downside of the robustness problems.
If you will let me just one more little thing.
Maybe we should move on to the next question, Armin, and then we'll hold off on the big questions for break. Go ahead, Frank.
Chat during the break.
I want to go back to your pandas. If you can go back to your pandas and ask a question that is a little bit loaded.
Looks like I can't go back.
Well,
but we can remember the pandas line.
There we go.
Oh, there.
So what I understood is that there is, for any such classification algorithm, there is a potential to overtrain and it being benign for all the reasons you get. I get that. So now that also implies here that there is an infinite number of ways, probably, that I can fool the algorithm and get something that the algorithm wrongly assigns by mucking in the space that is irrelevant, right? And at the same time, a human will always find the right answer. Now, if that is fact, and I'm going to hypothesize this for a second, doesn't that mean that deep learning has fundamentally nothing to do with intelligence? Because we're so much better and so much less fooled by adversarial, I forget what you call it, adversarial
perturbations. Yeah.
Perturbations,
right.
That there's something fundamentally different going on in this thing than in the computer.
Yeah, I guess the right response here is I don't know. you know, I don't think that, so, you know, this is certainly a shortcoming of the straightforward approach of minimizing logistic loss on a large training sample. There are cleverer things you can do. There are approaches you can take that don't have such huge sensitivity to these adversarial perturbations. I don't know what that has to say about you know, whether that means that we're missing something essential in these statistical approaches, you know, that we have in whatever machinery that we have for solving the same problems, right? I mean, that feels like a leap to me, maybe totally appropriate, but yeah.
All right, on that note, we should take a short break. We are running a little over time, so we'll reconvene at 10:50. And let's thank Dr. Bartlett again for a great talk. Introduce Mercy Asiedu. She's a research scientist for responsible AI at Google, and
oh, I guess I have this. Hi, everyone. Good morning. It's very nice to be here again from last year when I was interviewing and to meet so many familiar faces. So I'll be talking a bit about some of the work I've done on medical technologies and ML for global health and health equity. So to get started, a lot of proposals for mitigating bias in AI and health tend to start at this stage of what do we collect, what kinds of data do we collect, how do we prepare the data, and how do we mitigate bias during the data collection process, also along the model development process, evaluation, and deployment. And I think, in my opinion, what a lot of these processes tend to miss is that in a lot of areas of the world, there's limited access to the devices that are actually collecting and generating data. And this picture is from a hospital in Malawi, where there's a lot of devices that are kind of not working, thrown away because of lack of maintenance. And what that means is you don't always get data available just because of the access. Additionally, even if devices exist, it's very difficult to get access to health records due to the way they are stored in paper files, mostly, even though there's a transition to electronic health records, it's very slowly. And this is typically how health records are stored in a lot of smaller hospitals in Africa. And then there's also the case of disparate quality and use cases of devices that typical models are trained on. So take the mammogram, for instance, which is what this image shows. In high-income settings, you may have access to a lot of 3D mammography data, whereas when you go towards low-income settings, when these exist, it might only be 2D, and the distribution shifts in applying models from 3D to the impact model performance. So based on that, a lot of my interest is in mitigating bias through development of medical data generating devices. And some of the questions I asked was, how can we make medical devices that increase accessibility to healthcare and generate representative data sets? And so on that note, I'll talk a bit about work that I did at Duke to do just that in the context of cervical cancer screening, and also talk about some other works post-Duke. So just some background on cervical cancer, and this talk is very much an applications talk. So cervical cancer is a malignancy that starts in the cervix. It's in the lower part of the uterus and develops over a long period of time into it can develop over a long period of time into cancer. The note here, though, is that it takes a very long time to progress from time of infection to full-blown metastasized cancer. And I'm not sure why the title looks weird, but it's showing the mortality rate of cervical cancer globally. And what this shows is that there's a high incidence in a lot of low and middle income countries. And so 500,000 new cases of cervical cancer a year, there's a 55% mortality rate, and 85%, actually now greater than 90% of deaths occur in underserved settings because greater than 60% of women are not getting screened. However, as I mentioned, it's slow growing, it's highly preventable, and it's highly treatable. And even in countries like the United States, there's still disparities by state. And also, when you look at race, you have non-Hispanic Black women being twice as likely to die from cervical cancer as non-Hispanic white women. And part of this is because of this highly resource-intensive screening process, which involves the pap smear, where cells are taken from the cervix, diagnosis with a device called a colposcope, where an image is taken of the cervix, and interpretation is made with visual inspection and pathology, and treatment is done if that comes back as positive. So what we did was really focus on this aspect of colposcopy, which is used to image changes in the cervix, but it's also expensive, unwieldy, and overly sensitive. And the version of this that happens in a lot of underserved settings is visual inspection with the naked eye with acetic acid. It's cheap, and you can do this anywhere. It's highly beneficial for community-based screening, but it's very subjective. There's low data quality control because there's no data collected. So we took the clinical colposcope, which could serve as a replacement for visual inspection with acetic acid, and turned something that ranges from 50 to 150 pounds, costs up to $15,000, to something in the form factor of a spy pen. And the goal of this work led to the development of a low-cost speculum-free device for imaging the cervix. We did clinical validation studies and then developed diagnostic algorithms to look at automatic risk assessment to reduce the subjectivity and the need for experts. And I'll just go through this a bit quickly. So we initially developed the pocket colposcope, which has been FDA approved, and it's on the WHO list of tools for cervical cancer screening now, cost $500 to make, and found that it actually allows us to image the cervix on par as the 20,000 Lejeune optic colposcope that we're using at Duke. And then we took this one step further and went from saying, what if, based on not having to look at the cervix from outside the body and being able to insert a device to image the cervix, we could actually allow people to do this themselves and really empower cervical cancer screening and remove the speculum, which has been shown to be a barrier to screening. And just for some background on the speculum, it's used to expand the vaginal canal to look at the cervix and take an image. And it hasn't seen any significant change in over 150 years. And just for some context, the Apple computer, which was developed a couple of years after the speculum, has seen a lot of changes, and the speculum is still how it looks like. So we, through a lot of human-centered design processes, developed this coloscope. And this here shows for the first time a participant using this for self-imaging of the cervix. And we're able to have a global reach with these devices and with over 10 partners, screening about 1,000 women with both the pocket colposcope and the coloscope. And this allowed us to generate data for the next step, which was automated screening using the pocket colposcope and the coloscope. So with this, some background on screening uses sources of contrast, acetic acid for visual inspection with acetic acid, green illumination vascular imaging that highlights vasculature, and visual inspection with Lugos iodine, which turns cancerous parts of the cervix yellow, just at a very basic level. And we're primarily interested in features of color and texture. And so what we did here, this is a summary of the process, was take images taken with a pocket colposcope, perform pre-processing on them. So there was a lot of feature engineering here because we started off with very few images. So things like specular reflection removal, Gabor segmentation, and using k-means clustering to select a region of interest for further analysis. And then looking at color and texture from using approaches like Haralick's texture features. And from that, we extracted about 66 features from each image. And from that, we also selected a subset of features, which were used to train an SVM and a logistic regression classifier with ground truth of histopathology. And we also looked at different ways of combining the different contrast agents using methods where we call the parallel combination of VIA, where we just put in outputs from the SVM score to retrain another support vector machine, and the serial combination, which used more clinical decision methods that clinicians used. And what we found was that this receiver operating curve shows performance of the individual algorithm, so visual inspection with acetic acid, visual inspection with Lugos iodine, and the different combinations. And it also shows the physician's performances with specificity and sensitivity indicated. And we found that VIA and VILI, using the methods we proposed, actually performed on par with clinicians with ground truth histopathology, but when you combine them, you actually had an improved performance. And clinicians were also looking at both contrasts. And we could also see an increase in accuracy with the algorithm compared to the physicians who had over 15 years of experience. Another area we looked at was combining all three contrasts, so adding in the green light imaging to the VIA and VILI. And again, we saw the same thing where despite limited data, as you increase the number of contrasts, you got an improvement in accuracy. However, as you can see, the most amount of data we had here at that time was 134 images, and we worked on increasing this. So now we have over 1,000 images from different countries, and this allowed us to explore more deep learning type models on this larger data set. And we used a cervix detector model that we developed using just a basic YOLO segmentation, and then from that, selecting a region of interest that was then input into a classification model for outcome. And for this process, we also looked at combining the different contrast agents and found on a holdout test set that what we expected from the previous feature engineering heavy approaches with increasing performances from increasing number of contrasts also held true here, where we achieved an AUC of 0.81 with acetic acid, 0.78 with just the green light imaging, and when we combined that, we had an AUC of 0.87. And this work was done with collaborators in Peru, in Lima, who usually go out to different markets and neighborhoods to perform screening, and we did a lot of interviews, asking them about feedback that went into developing the devices. And we also did work with the Greater Accra Regional Hospital in Ghana, where we had women use the device for self-screening and had overwhelmingly positive feedback. And that has led to the startup called the Color Health Foundation, which is producing and marketing the devices. I don't know if I have more time, but the next thing I wanted to touch on quickly was on some work that was done in ultrasound imaging to look at improving low-cost portable images from low-cost portable devices. So they kind of had the quality of images from high-cost clinical devices. And what was done here was taken using a clinical ultrasound. You can kind of see differences. You can simulate differences from low-cost devices which have low voltage outputs. And those images can't really look at features that are very deep in the body, whereas clinical devices can. So these are because of power outputs and exposure, and these are limited by the size of the probes and the cost of the probes, but also limited by certain thermal and mechanical bioeffects that the FDA regulates. So what we wanted to do was look at whether a machine learning software-based approach could easily translate these low voltage images to high voltage ones with potential applications overcoming the FDA power limit, but also looking at things like fetal ultrasound and imaging fatty tissue and portable ultrasound as well. So for this, we used a simple generative adversarial network and collected data using vascular phantoms from a clinical device that was set at 20 volts and 70 volts power to simulate the differences between the portable and the clinical devices, and did some data processing. So it turned out we couldn't just put the images through a generative network, which in this case we used conditional GANs, but doing the the GANs weren't able to learn the features that we wanted them to. We didn't want a simple multiplication that would also increase noise, but we really wanted the GANs to learn to improve signal to noise ratio in deeper settings and not increase the noise in deeper parts of the image. So that's what the data pre-processing here allowed us to do. And just skipping because of time, in the end, what you see here is low voltage images at 20 volts, and you can see the noise in the red boxes and the model output and the image at 70 volts. And what we realized was with training, we're able to improve the signal to noise ratio for low voltage ultrasound images so that they reflected images that were generated from high voltage ultrasound images. And we found that both in hypoechoic, or the darker areas, and hyperechoic, which is the bright spots in ultrasound imaging. So what I'm currently doing is exploring other ways to bring data to for ML applications for health in West Africa, and part of that has been to develop this application through gaphealth.ai, which has been looking at patient-centered ways to store and collect data, but also enabling patients to own their data and decide whether they want to use that for research. And it's currently being deployed in Ghana and the Gambia, and has 200 plus providers and greater than 900 patients. So the purpose of this is to say, if we don't have electronic health records that work in the same way as they would in high income settings, can we kind of using mobile technology overcome these and empower patients to be owners of their data and to manage that access. Other items I'm looking at is understanding and continuing to understand and account for distribution shifts in foundational models for global health. So Another iteration to the machine learning model is looking at different biases across different aspects of development and understanding that in the African context. So looking at African-specific axes, African-specific social attributes, socioeconomic attributes, and health attributes, and then bringing that to health and looking at where these impact different aspects of health. So whether it's in vitals, written notes, medical imaging, or genomics. And I'm really excited for the direction of that. So thank you.
Thank you, Mercy. I think in the interest of time, we'll just hold off on the questions till the lunch break. And we'll next have Rose Yu. She's assistant professor in CSE and HDSI.
Hello. Hi. Good morning, everyone. Sorry about the voice. I'm just recovering from the cold. So my name is Rose Yu. I'm assistant professor in the computer science department and also HDSI. So my research focus on physics-guided AI for large-scale spatial temporal data. Large amount of space and time data arises from all type of fields, from public health, transportation, climate science, and different areas of engineering. So the continuous nature of spatial temporal data make it very different from traditional applications in machine learning, such as static image data or discrete text data. And the mission of our group is to advance machine learning towards learning from large-scale spatial temporal data and capture real-time dynamics, and hopefully use these tools for more efficient real-time decision-making in science and engineering. The type of research paradigm that we have been developing over the past few years is called physics-guided AI, because physics develop first principle method that uses model-based approaches to describe space and time phenomenon. There are a lot of tools in physics, such as tensor networks, differential equations, or the concept of symmetry that can help us understand the space and time dynamics. But unfortunately, physics-based models often assume very strong assumptions of the underlying dynamics, making them very infeasible for the real-world phenomenon. On the other hand, simulating physics-based models for high resolution and complex dynamics is also computationally expensive. On contrary, machine learning methods offers this paradigm that is much more flexible. They're based on statistical inference, and they're developing data-driven models. So in machine learning, we have graphical models, neural networks, and variational bayes. So machine learning models are learning from data. Therefore, they make very little assumptions of the underlying dynamic of phenomenon. And machine learning models are very scalable. With the current development in automatic differentiation and parallel computing, we can scale to large data sets much easier than before. But the problem with machine learning methods is they don't understand physics. So it is very difficult for us to guarantee the predictions of our method to generate are trustworthy, and then can be relevant to domain science and be useful for our scientists and engineers. So therefore, our goal is to basically combine the best of two worlds together to encode inductive bias, improve generalization, and improve sample complexity of learning, and eventually increase our trust in AI. Just to give you some vignette of what has happened in our group in the past few years, we worked with people in climate science to speed up turbulence simulation in climate field. Just to give you a sense, simulating this kind of turbulence usually takes a couple months, and we developed a physics-informed deep neural networks that combine techniques from computational fluid dynamic simulation and deep learning to speed up the computation of fluid forecasts. Our method is not only fast, but also conform to the kinetic energy spectrum of the predicted turbulence. And this method has been deployed by people in Los Alamos labs to simulating their turbulence dynamics. We can also use this kind of model as a digital twin to understand different type of complex turbulence in climate or the ocean, and we can allow the model to change given different type of input in a controllable fashion to generate very realistic turbulence given arbitrary conditions. Just to give you a sense, we also fortunately received the major award from Department of Energy, and I was a PI of a 3.6 million Department of Energy grant on scientific machine learning. And just a few months ago, we hosted our very first scientific machine learning symposium at UCSD, co-sponsored by HDSI, Computer Science Department, and SIO. Another example, so in collaboration with EMA, where is Ian? And we have been working with CDC to forecast the COVID-19 dynamics and speed up the scenario generation for the pandemic. In fact, we developed this hybrid physics-based model to generate what-if scenarios for different type of COVID cases. And our model was able to emulate a very complex stochastic simulation model developed by computational epidemiologists, but at a much faster rate. And more importantly, our model not only can emulate the prediction of a trajectory in terms of number of cases for the next 4 years, but also can emulate uncertainty in terms of confidence intervals in this prediction. And this is particularly important for assessing risks and quantifying uncertainty in real-time decision-making. And our team actually was ranked #1 in terms of uncertainty quantification among 40 also national teams participating in this CDC forecasting challenge. We also worked with Professor Mike Gilson from Pharmaceutical Sciences to develop hybrid models to generate better drugs. In this case, we developed a generative model to simulate, to generate novel drug candidates given any controlled desirable properties such as binding affinity, synthesizability, and QED scores. The candidate drugs of our model actually lead to better binding affinity than some of the drugs on the market. So we're actively working with people in experiments trying to realize these candidates into experimental results. With some more people in physics, we have been exploring this idea of symmetry. And recently, we have some very exciting new results that we are trying to develop deep learning models that can automatically discover the underlying symmetry from data. In this case, we're looking at the high energy particle physics data that our model can automatically discover this very interesting Lorentz symmetry from the model and realizing our dream of AI scientists. We have been working with companies in biomedical domain where we're trying to develop hybrid physics-guided models to achieve real-time control of smart blood pressure, And in this case, we're taking the real-time sensing data from this heart pump and then develop smart algorithms to control the blood pressure in real time. And our effort actually have helped the company to achieve the FDA approval to stream their data into this into their Impella console. So these are some examples of our research going in our group, and this would not have been possible without the generous support from HDSI and Computer Science Department. I'm just very fortunate to be part of this endeavor, and you can reach out to me with any questions, and thanks for the sponsor for this research. And again, happy birthday. Congratulations, Rajesh and HDSI.
We can take maybe one question. All right. I think that's fine. We should get going. Right. I'd like to invite Tauhidur Rahman. He's assistant professor in HDSI. Next.
Should I use it? All right. All right. I have a surprise. All right. Sure. All right. Good morning, everyone. First of all, thank you. Thanks for giving me this wonderful opportunity to speak about my research today on this historic event, right? My name is, once again, Tauhidur Rahman. I'm an assistant professor in Halıcıoğlu Data Science Institute here at UCSD. I'm also the director of Mobile Sensing and Ubiquitous Computing Laboratory. And today, I'm going to talk about harnessing health signals with large-scale mobile sensor data for tackling complex societal challenges. So let's at first talk about mobile sensor data. Thanks to the ubiquity of mobile devices in our lives, and thanks to the availability of a wide range of sensors, built-in sensors in many of these mobile devices, really seen a rapid expansion and adoption of mobile sensor data systems in the health space. If we look at recent works coming out of both academia and industry, we'll be able to see that all their existing evidence that are pointing to the fact that mobile sensor data can fundamentally enable next generation healthcare by redefining how we monitor health conditions, how we track effects of treatment, detect incidence of diseases, and administer just-in-time adaptive health interventions. So now the question is, what is behind such a resounding success, right, of mobile sensor data systems? And if you look for the answer, we'll find it comes down to digital biomarkers. In fact, if we have seen recent years, many of the built-in sensors that we have in our smartphones or wearables have been successfully used to create an array of digital biomarkers that can successfully capture internal physiological and behavioral processes. And while we are making big strides in the mobile sensing technology space, as a society, our generation is going through unprecedented time and facing complex public health challenges. As the pandemic spread across the country in the 12-month period that ended in April 2021, more than 100,000 Americans died due to drug overdose. There has been almost a 30% increase in drug overdose-related mortality from the previous year. This, in fact, marks the first time when the number of overdose deaths in the United States has exceeded 100,000 a year, which was more than the total toll of car crashes and gun fatality combined. So now, a natural question to ask is mobile sensor data living up to the expectation, right? Is the mobile sensing device, sensor systems, and the digital biomarkers that we have in our disposal really helping us, enabling us to tackle some of these tough social problems? And if you look for the answer, we'll find that there are gaps, right? We still lack in mobile sensing mechanism and data science methodology to create new variants of digital biomarkers that can allow us to model what we call early syndromic indicators. And many of the existing digital biomarkers broadly are more associated with slightly late indicators. And unless we have what we call early indicators, we'll not be able to use many of these mobile health sensing technologies for early detection or just-in-time intervention. And fundamentally, this is a data science problem, right? And now, if we also steer our attention from individual person-level mobile sensing problems to population-level sensing problems, we'll see a slightly different set of, again, data science challenge. And the main challenge here is how we can harness population-level syndromic signals with an array of person-level mobile devices at scale. And one of the main reasons behind that is that the ubiquity of personal mobile devices does not directly guarantee that it will be an effective means for population-level syndromic data aggregation. And if a significant number of people either do not have access to that desired mobile device or do not feel comfortable sharing the data, the resultant aggregated population-level syndromic signals may not be representative of the community or the population-level statistics anymore. Thus, we are left with this low signal-to-noise ratio signal, which fundamentally limits our ability to make data-informed, effective community-level disease forecasting. And in our research, we aim to solve these data science challenges by developing what we call smart and connected mobile sensor data ecosystem, right? emphasis on the ecosystem for sensing early health indicators, both from individuals and communities at scale for generalizable and accurate predictive analytics. And in this blob of text, I want to particularly highlight 3 key terms, which are respectively earliness, scalability, and correctness. And these 3 terms essentially highlight 3 major design considerations when it comes down to creating, mobile sensor data ecosystems. And the challenge here is that these 3 key terms doesn't go hand in hand, and we have to be innovative in terms of creating novel variants of mobile sensor data ecosystem that can simultaneously maximize all these key terms together. And with that kind of research vision and philosophy in mind, Mosaic Lab have been doing its research, and today in this lightning talk, I'll give a quick buffet-style overview of some of the recent projects and ideas that we're kind of thinking about in the lab. One of the big emphasis or interest of the lab has been substance use disorder and drug overdose. And as you may already be aware of, many of the drug overdose-related mortality can be associated with what we call opioid addiction. Now, in order to understand opioid addiction, right, we have to really understand the downward spiral of opioid use disorder, right? So first of all, what is opioid? Opioid is a class of drug that binds to brain and nervous system, right? These are essentially can provide us temporary relief to recurrent pain, right? And the problem here is that repetitive use of the drug changes the brain circuitry in such a way that give rise to attentional fixation, stress and negative emotion, and rumination of pain, which in turn promote, again, recurrent use of opioid use. And very soon after that, an individual may find in this downward spiral or downward trajectory and lose control over opioid use and develop opioid use disorder. And now, as you can see in this graph, reinforcement of opioid use or repetitive opioid use is a leading indicator of loss of control over opioid use. And just by monitoring opioid use, we can actually, it can provide us with an early warning mechanism for opioid use disorder. Now, that doesn't exist. No objective measure exists to passively and continuously monitor opioid use. And in our work, we have proposed OpiTrack, a wearable-based opioid use tracker that leverages multimodal physiological signals that can be captured with a smartphone and can be, by using advanced, basically deep learning, more specifically temporal convolutional attention network, we can kind of map it to, we can use it to detect opioid use within a window. And on top of that, we can also predict a precise administration moment within that 45 minutes window, which we have happened to have used for this particular project. Now, when it comes to administration of digital therapeutics, right, or just-in-time adaptive health intervention, detecting opioid use alone is not sufficient, right? Why is that? Because by the time someone has consumed opioid, it's already too late for any intervention. However, if we can effectively detect craving moment, and this is the leading indicator that is we're missing, right? If we can detect the craving moment, that can give us an opportunistic moment of opportunity for us to trigger just-in-time intervention so that the individual can break out of this addiction loop. And we also have been doing, have demonstrated that just by looking at morphological features of physiological signals, specifically cardiac and respiratory signals, from a wearable chest band, we can actually predict craving with fairly high accuracy. Now, building on top of all of this works, we aim to develop a closed-loop mobile system that can not only detect opportunistic moments, such as craving moments, but also can select optimal intervention based on a reward function. And in a very recent work, we have demonstrated that this reward function, right? You can think of it in the reinforcement learning reward function, right? We have demonstrated that this reward function can be actually learned by looking at smartwatch data and by modeling effectiveness of digital just-in-time interventions, and we can do it reasonably accurately. Now, I'm going backward. All right, so now, so far, I'm gonna shift gear a little bit in the next 5 minutes. So far, we have been talking about individual level mobile health problems. If we steer our attention from individual level to population level, we'll find that time, the notion of time actually also play a super critical role here. timely access to data and timely response dictates the success of any public health response, right? However, ensuring these two things, timely access to data and timely response, is challenging for the fact that public health data aggregation is super complex. We collect data from complex heterogeneous sources. It takes actually a lot of time. On the image that you can see, we can see a public health officer, collecting in Indonesia, collecting dengue information. And you can see these kind of technologies still being used, right? Like making phone calls and manually writing that piece of information on a whiteboard. This is what public health look like on practice, right? And you can see it takes a lot of time, and it in fact prevents timely public health response. And let's try to now look at this problem in the context of flu surveillance. US CDC primarily collects aggregated data from hospitals, an array of hospitals and clinics, and due to complexity of data collection and aggregation, CDC actually has about 7 to 14 days of reporting delay, and which is actually a hallmark of, which is essentially a major vulnerability in our flu surveillance technology. So the fundamental question that we asked is, can you develop a mobile sensor data ecosystem, again, emphasis on ecosystem, to capture early syndromic indicator directly from a community, and all that without requiring any active participation from the community that we are trying to surveil. And we have made, in order to address this problem, we have proposed FluSense, a contactless syndromic surveillance platform from influenza-like illness. So far, we have made 2 prototypes. I actually have brought 1 prototype just to, I have a picture sometimes just to give you the right inside. This is how the prototype looks like that we have deployed. It actually consists of very low cost hardware, Raspberry Pi. It connects with interfaces with several sensing technologies like microphone array. It also has a thermal camera in the generation 2 version. We have introduced a radar to capture motion signatures. And it also have all the edge computing capabilities like local storage. We have used some Intel product. Intel NCS2, and also has the local cloud computing capabilities. And the high-level idea was that was to deploy the contactless syndromic surveillance platform in specific public spaces, not everywhere, specific public spaces where a large group of people naturally congregates. Examples of this specific location can be, cafes or libraries and large classrooms where we kind of get to sample 15 or 20 minutes of large cross-sectional population's daily lives. And we could also potentially put it in public transportation systems or transportation hubs. And just by under the hood, the box essentially kind of captured crowd size estimation as well as other syndromic signals like cough sensing. And by that we have demonstrated that multiple of these generated syndromic signals that can be captured in real time exhibited strong correlation with total flu counts and laboratory confirmed influenza infection in a college campus community. And we have also replicated it in the context of COVID-19, and we found statistically significant evidence that crowd level cough counts is a reliable syndromic indicator for COVID-19 burden in the context of a hospital emergency clinic. What was particularly noteworthy was that total cough count was statistically a better syndromic signal than fever in a hospital clinic setting. Generally, fever is thought to be a prime indicator of COVID-19, right? With that, I would like to end my talk. Thank you so much thanks to Halıcıoğlu for giving me this opportunity to talk about my research, and thanks to the funding agencies for allowing me to do the research. Thank you.
Thank you, Tauhidur. Our next speaker is Professor George Sugihara. He's the McQuan Chair in Natural Sciences at SIO and also a professor at HDSI.
we good? So can they can't see anything. What do you see now? They don't see anything. I mean, I can see this. They don't see anything. You still see the. So there's nothing on the screen. There you go. Okay. You're just gonna have to get this paper to go forward. Okay. So let me do this. Sorry about that little interruption at the beginning here. So inferring causality from observations is one of the deep goals in science and arguably extends to all aspects of scholarly inquiry. The issue is one that's vexed and challenged scholars across a wide range of disciplines. So while we're all familiar with Berkeley's famous dictum, correlation or coincidental association does not necessarily imply causation. What most of us don't realize is that the inverse and actually the converse is also true. So namely, that the lack of correlation does not imply lack of causation. Let's look at an example. So consider these two time series. One may be interest rates, the other, say, is housing starts. They are obviously correlated, but how well does this hold up? Here we roll forward another decade or so, and except for this aberration, I don't know, so you can't see my cursor, except for this aberration, where things are temporarily reversed, our hypothesis remains pretty much intact. However, if we roll forward another couple of decades, we see that these two variables are uncorrelated, even though they are in fact deterministically coupled. These time series arise from a simple coupled logistic difference equations. So if you look at the output, you might think that they're unrelated, even though they are in fact deterministically and causally related. So, plus, not only does correlation not imply causation, but the inverse is true. Lack of correlation does not imply lack of causation. Biological systems are particularly perverse on this issue by exhibiting mirage correlations, correlations that come and go and switch signs, as we saw in the model example. So here's an example from the real world. Red tides are a classic local mystery. It's one of the most conspicuous environmental consequences at SIO's doorstep, which is somewhat of an embarrassment, as we've not been able to predict or uncover a mechanism for over a century. These are data actually from the SIO peer, and as you can see, the green chlorophyll spikes and the blue temperature anomalies are positively correlated for over a decade. But if we continue observing, they become negatively correlated and then uncorrelated, there's a little gap there where we lost funding. So in fact, no correlations have been found with any environmental variables. So as anyone who has tried to make models based on correlations and then actually predict with them can tell you, mirage correlation is ubiquitous. So these kinds of models in finance have caused a lot of people to go belly up. All right. So it turns out that this fact is not well known. It contradicts a popular unconscious view that correlation is necessary for causation. So this is Edward Tufte. This was a Wikipedia page that has since been taken down. Okay, so how to address this? Here's a brief video animation to set the stage. The narration is by the late Lord Robert May. We're not getting the audio.
Depends on the state and dynamics of the other two components. You can think of each component, for example, as being species, foxes, rabbits, grasses, and each one changes depending on the state of the other two. So these components, shown here as the axes, are actually the state variables or the Cartesian coordinates that form the state space. Notice that when the system is in one lobe, X and Z are positively correlated, and when the system is in the other lobe, X and Z are negatively correlated, the other wing of the butterfly. We can view a time series thus as a projection from that manifold onto a coordinate axis of the state space. Here we see the projection onto axis X and the resulting time series recording displacements of X. This can be repeated on the other coordinate axes to generate other simultaneous time series. And so these time series are really just projections of the manifold dynamics onto coordinate axes. Conversely, we can recreate the manifold by projecting the individual time series back into the state space to create the flow. In this panel, we can see the three time series, X, Y, and Z, each of which is really a projection of the motion on that manifold. And what we're doing is the opposite here. We are taking the time series and projecting them back into the original three-dimensional state space to recreate the manifold, the butterfly attractor.
Okay, so to summarize, time series are observations or projections of motion on an attractor. And constructing attractors from time series is really the basis of the empirical dynamic approach. And the aim here is to produce mechanistic models from data using minimal assumptions. So this all came along before we realized that you should be adding more parameters to your models. So it's really based on this notion of minimalism, which I can tell you was a pretty important guiding principle for managing financial assets. All right, so the essential thing to realize here is that attractors are not exotic. If there are rules governing the system, if nature is not purely random, there is an attractor of some sort. The attractor and the equations are essentially equivalent. Both represent the rules governing the relationships among variables, and depending on when they're viewed, these relationships can appear to change, giving rise to mirage correlations. The important difference between attractors and equations is that the attractors can be constructed directly from data. They portray the relationships as they are, as they're realized in our observations, rather than as we think they might be. So let's look at a real example. These are experimental data on expression levels of two genes that show no obvious relationship to each other. They are uncorrelated. However, when the measurements are connected by time, they are clearly interrelated. We see the skeleton of an attractor emergence. So time is really essential to see the structure here. Note, however, that there are points where the trajectories cross, points where the fates are non-unique, these singularities, where the embedding is not deterministic. However, this disappears when you include another causally linked gene, in this case, CLIB2. This shows the fully unfolded attractor with the three coupled genes. But how can we know in advance that these three uncorrelated genes actually belong together? The answer, without explaining it, was that we can use a method based on a general approach similar to what we just saw. It's one that involves building dynamic attractors from data. Although it was motivated by ecology, this method allows us to address a central problem in genomics, which is what is the causal network that coordinates gene expression? And in particular, it allows us to address the difficult problem of identifying causal networks for genes that show no correlation to each other. Such non-correlated but strongly coupled genes are thought to be important in controlling gene regulation. So what was really nice about this problem is that for the first time, we actually have the opportunity to verify the causal linkages that we identify using this method, CCM, using experimental manipulation, so I think experiment is really the only way that you can really determine causation. All this other stuff is sort of a proxy for building like a legal brief that you believe something is causal. All right, so we can test whether experimental manipulation changed the dynamics, i.e. whether it alters the attractor of genes as predicted. So the solid line in this diagram is the wild type attractor, and the dashed line shows the attractor after experimental manipulation. And you can see that it's actually distorted as predicted. So these are things that would be undetectable because they're essentially not correlated with each other. So the idea here was we took this basic idea demonstrated in this one case and carried it out in two experiments that each involved hundreds of genes that were uncorrelated with each other and with their experimental targets. So the final results actually were very good. I'm just showing what we found here. So the 72 to 80 to 78% success rate compares well with the then industry standard DREAM5, which only has a 3% success rate. This really is, I think, potentially a game changer. Basically, it suggests that there's much to be gained by treating gene expression as a dynamic, organized process rather than simply as an atemporal statistical one. So what's true for gene expression is broadly applicable across many fields of natural science where experimental verification of causal linkage is not feasible. For example, in ecology, where other kinds of verification are needed, such as out-of-sample prediction. Okay, as mentioned earlier, the red tides at Scripps is something that no one has been able to predict. Although we know in principle and by experiment, maybe a half a dozen or so Scripps theses have showed that certain environmental drivers should be important. In the field data, no obvious correlations have been found linking these environmental variables to chlorophyll A, which is our sort of proxy for the red tide. This was a topic, this was actually the topic for a project class held at SIO before the pandemic. So this is what you're going to see as student work. Okay. This was exactly the case with the temperature anomaly we saw earlier. There are no fixed correlation between the suspected environmental drivers and algal blooms. Okay, here are the candidate environmental drivers. They can be grouped into two loose categories: variables related to stratification and mixing, and variables related to nutrient history. Although we can't do the field experiments to test this, we can use out-of-sample forecasting with these simple embedding models that use these variables to show if they predict. For this class project, the available data that was used to build the models ended in 2010. So the subsequent water samples were taken, but they hadn't been analyzed or counted. Okay, so let's see. Okay, so you can see there's no clear evidence of correlation, but when you apply this causality test, nearly every variable is significant. So, all right. So if you use these and you make a model and you now predict data that was previously unavailable, you find it actually seems to work reasonably well. So our understanding of causal mechanism is therefore supported by our ability to make reasonable, fully out-of-sample forecasts. All right. So this is my final example, was another student-led project. Nicole Nova was a student at Stanford, now at Princeton. The idea here was to use environmental and dengue incidence data provided by the 2019 Dengue Forecasting Challenge to identify causal variables and to use them to make simple EDM forecasts. The objective of the challenge was to test out-of-sample predictions. All right. Following the challenge protocol, time series on possible environmental drivers and dengue incidents for 1990 through 2009 were made available to construct models that were then tested out of sample to make 8-week ahead forecasts for 2010 to 2013. Okay, so this shows how the model stacked up. There were 4 performance metrics used in this challenge: peak incidence, peak week, seasonal incidence, and some composite, basically. The 16 other contestants, A through P, the model that did best is highlighted in bold, and in this case, the error score values closest to 0 indicate higher forecasting skill. So a good result would be 0 in each of these categories. And so what we find actually is that this mechanistic data-driven attractor-based model outperforms all of the models from the forecasting challenge in all categories. So predicting peak incidence, peak week, seasonal incidence, and summary metric for all performance targets on average. All right. So Nicole was so this paper did quite well in terms of the forecasting challenge, and Nicole actually was acknowledged by getting the being actually runner-up for the Murray F. Buell Award for the best student presentation at ESA, which is the ecologists' big meeting. Okay. All right. So I leave you with this commentary that appeared in PNAS. and I think was a nice confirmation of this data-driven approach. The abundance of data and the demand for utility are important causal drivers, I think, of scientific progress. Data science and the increasing availability of data across disciplines makes this all possible. And this is my final little joke slide, but not totally. So I think with more data, we're being actually held to a higher standard. Science is being held to a higher standard of proof to verify what actually does work versus what we think should work. Thank you.
Thank you, George. And as education is also a big part of HDSI, we'll next have Professor Yoav Freund from CSE and HDSI to talk about class projects.
So this is a title from a paper that appeared in 2017 by the World Bank. And in it, they said, using high-resolution satellite imaging for estimating economic well-being. So if wild suggestions have been made, in using machine learning, this is definitely one of them. And so what I did in my class was to basically set this problem as a challenge. Here I'll give you just a few examples just to see what it looks like. So this data was collected from satellite images, and there was also collected information about the wealth of households in areas. This is all was done in Africa, sub-Saharan Africa, 23 countries and 20,000 images. Pretty big data. The area of each image is about 4.2 times 4.2 mile per image. So just to kind of give you a sense about what that is, this is an area around here, around UCSD, that is 4.2 by 4.2 images. And what you have in terms of the image, the image is reasonable size, is 200 and 224 pixels, which means that each pixel is about 30 meters on a side. So each pixel only captures a very rough and big area. So what helps is that it is done in 8 channels. So here I'm first just showing you some images from rural areas that were captured in RGB. So you clearly can see if it's poor or rich. And then here is another set from urban areas. And you can see that these look quite different. And indeed, in order to make the problem reasonable, we separated the urban from the rural, because otherwise urban is clearly, once you know that it's urban, it's much richer. So what helps us do the work, what gives us a fighting chance of this, is that it's not just the RGB, but rather there is 8 channels that you get from these satellites. And while some of these are the standard RGB, and then near infrared, short infrared 1 and 2, and temperature, the last one is actually the most informative one, was identified about 10, 20 years ago, that if you look at the night light, at the amount of light that comes out of an urban area or an area in general, and that is a good indication about economic activity. So this one signal is one of the most informative, but we do significantly better. Here is just to show you that the wealth distribution is very different in rural and urban, and therefore we use two different problems. One is to find above or below the median in rural, and one is above below the median in urban. Okay, so this was done in this class called Data Analytics Using Sparks. And there are two subparts to this class. There are two separate classes. One class was in computer science, CSE 255, and the other class is part of this new online study that we have in online masters in data science. In each one of these classes, we have a winning team to which I'll give the prize. And this was done based on the highest average rank or the highest accuracy. There's more that went into it, but I'll skip that. So that's it. And now I'd like to invite to the podium the Angry Bird team from CSE 255. Okay, so Angry team, please come here. Later. Right here. All right, and for the DSC team, we have one representative because the others are around the world, and so Ryan Newbury. Okay, that's it.
All right, we are now at lunch, so we will please do reconvene at 1:30 for our next keynote. And let's thank all of the participants in this session for great talks and also for trying to stay on time. Thank you. Hello. Yeah, if I can have your attention, please. We are going to get started soon, so please have a seat. All right. Let's go ahead and get started. Can I have your attention, please? All right. I'm going to introduce our next keynote speaker, Professor Eric Topol. He's a professor in the Department of Molecular Medicine and an executive vice president at Scripps Research and the founder director of the Scripps Translational Research Institute. Dr. Topol's work melds genomics, big data, and information technologies and other digital health technologies to advance the promise of personalized medicine. He's a widely published and influential researcher with over 1,000 articles, research articles, and many popular books, as well as research books to his name. He's among the top 10 cited researchers in medicine. Prior to joining Scripps Health a few years ago, he served as the chief of cardiovascular medicine at the Cleveland Clinic, and he founded a new medical school and led the organization to be the #1 center for heart care in the nation. Among many other honors, Dr. Topol is a member of the National Academy of Sciences. So let's welcome Dr. Topol.
Thanks very much, Vineet. Does this mic work? Is it okay? I'll just use that? No? Okay, how about this one? Okay, I guess I better use this. Well, thanks very much for having me, and I'm pleased to join this 5-year celebration. And if I can get back to the first slide. Congratulations on that. We have the great privilege of working with Raj and the group as part of our Clinical and Translational Science Award Hub, and we're thrilled to have that opportunity and do some joint training of some of the young folks that are coming along the way to be leading data scientists and AI scientists in the future. So today, what Raj and Vineet asked me to address is where are we headed with AI and how it will change medicine. Obviously, this has been an area of intense interest since ChatGPT was first available in November 30th last year to the public, and within 90 days it already accrued more than 1 billion unique users. But the question is, what will this and subsequent large language models do for healthcare? So the first thing to point out is that medicine is very inaccurate. Besides what I have here, just think that 50% of doctors are below average. Now, if you remember that, you know there's room for error, and the errors are very frequent, such that in our lifetime, each of us will have a major diagnostic error. Each of us, no less more than one. And when a physician thinks of the diagnosis in the first 5 minutes, the accuracy is very high. But if that diagnosis doesn't come to the physician, it drops down precipitously. What's the average length of time a physician spends with a patient? 7 minutes. So that doesn't give a lot of room for margin for error. And then the other thing is about the hubris of physicians, because when the autopsy is done and the diagnosis is tried to match up with the physician's pre-mortem diagnosis, it's wrong 40% of the time by hard criteria from a pathologic exam. So everybody talks about this term precision medicine. That is a really stupid term, because if you make the same mistake over and over again, it's very precise. We don't need that. We need accuracy in medicine, and we don't have it. Now, there are 2 ways to get there, and I don't know of better ways than this, and these are past that provide lots of indirect ways. Like, for example, if you have more time with patients, you have more time to think, that in itself would help. How do we get more time, the gift of time, which should be the primary objective, to repair, restore, and improve upon the patient-doctor relationship? Well, for several years, the deep neural network architecture was the only thing we had to work with in medicine. And of course, as you know, that was spearheaded in many ways by Geoffrey Hinton and his colleagues that were awarded the Turing Prize a few years back. But more recently, back in 2017, Google researchers came up with the transformer model, which is the basis of large language models. And this is really setting the stage for another era of AI as it pertains to healthcare, as we'll review. So both of these can improve accuracy, but really the deep neural network's major impact has been improving accuracy of medical image interpretation. That's the sweet spot of what we have so far that's been validated. And so when I use the term machine eyes, machines don't have any eyes, but they see better than humans when they're trained, far better than humans, than doctors, than specialists. So this was a headline back in March in Hungary, of all places. They were using AI to find these tumors, breast cancers that were missed by physicians, radiologists. But the story is across every type of medical image. And these are scans like an X-ray, whereby when you give it to the radiologist who's an expert in X-ray interpretation, they can miss what the AI picks up when it's been trained by hundreds of thousands, if not millions, of chest X-rays to pick up the nodule that was proven to be cancer. This is NYU, which is this week is going to make another major contribution in this field. But this was about the largest study of mammograms, which are a very frequent source of errors, false positive, false negatives. And they did the largest study to show that the radiologists could have far better accuracy when helped with AI interpretation. Now, it isn't just that every type of image, whether it's nuclear, MRI, CT, X-ray, ultrasound, can be improved with deep neural network interpretation. But it's the things that we don't even look for as physicians when we look at a scan. And now this is actually quite remarkable. So when the retina images are inputted to deep neural networks, it can detect with accuracy kidney disease, blood pressure control, glucose control, precursor images that reflect high risk of developing Alzheimer's, heart attack risk, the calcium score of the coronary arteries through the retinal vessels, hyperlipidemia, and liver and gallbladder disease. That's a gateway to most organ systems of the body just through the retina. That's extraordinary, none of which could be detected by ophthalmologists or physicians of any type. Now, I'm a cardiologist, and the ECG is something I've been reading, and I love to read, 35 plus years of reading ECGs. I can't tell you the sex or the age of the patient, or the hemoglobin, or the ejection fraction, or some difficult diagnoses, but moreover, I can't tell you the extent, severity of valve disease, whether the person's going to get atrial fibrillation, whether the person is going to get diabetes from the ECG. Or what is the filling pressure of the left ventricle, whether the person is hyperthyroid without a thyroid function test, or whether there's kidney disease. Just to give you a flavor of what machine eyes can do when they're trained properly. Now, a gastroenterologist, you don't want to go today to have a colonoscopy without machine vision, because it's been shown through many randomized studies that the pickup of polyps is far better with the support of real-time machine vision. And not only does it pick up the polyps, but it'll give the proportion of likelihood of it being cancerous to do the biopsy in the first place, to avoid unnecessary biopsies. And this is standard practice in some countries in Asia, but still is rarely being done here in the United States, unfortunately. This is a clear, validated approach to improve diagnosis. And by the way, it was recently shown that the gastroenterologists that are doing procedures all day long, their detection rate gets worse and worse throughout the day. So if you want machine vision, you sure want it if you're going in for a colonoscopy in the afternoon, okay? Okay. Now, there's another side of this, and that is that the scans that we read out have a lot more information that's being left in the scan, which can be picked up through machine eyes, such as whether the person has diabetes from the abdominal CT or the risk of heart disease from a mammogram, all sorts of things. It's really pretty striking. Someday we'll get that information, glean all that useful information. Now, that was the deep learning era. Now with transformer models, we can go much broader, multimodal AI. So what we're talking about here is being able to take not just images, but language, text, speech, videos, anything, any types of input. That little purple dot at the right top is the trillion parameters of GPT-4, which is the first truly multimodal large language model. So this is a big advance, much more perhaps than people realize, the gap between GPT-4 and ChatGPT and other concurrent large language models. This is just like the mRNA vaccines, nanoparticles that took 30 to 40 years, and people thought, oh, all of a sudden there's these COVID vaccines. It's the same story here. This isn't something that happened last week, last year. This has been incubating over many decades to get to this point. And if you just look at GPT-4, we're looking at over 10 billion flops, 10 petaflops. And you can see on a linear plot how that compares to PaLM, which is a pretty reasonable peer generative AI model. It's a big jump. And this is just a recent summary. So we've gone from parameters, which are really the interactions in the model, from ChatGPT of 100 billion to PaLM 2 or MedPaLM to GPT-4, which is at this trillion level mark. So how did we get here? Well, let me ask you this. How many GPUs are needed to pre-train GPT-4? How many GPUs? Anybody know? It hasn't been released by Microsoft, but I wanted to get your guess about, what do you think, Raj? Anybody? 10,000? Keep going. Keep going. Erwin, what do you think? Well, not quite. 30,000 GPUs. 30,000. Who has 30,000 GPUs? Who can even cool the place that has 30,000 GPUs? That's what we're talking here. We couldn't have done this without massive doesn't even do justice. The flops, self-supervised learning. No longer in medicine, especially, do we have these models where the inputs are all annotated. This is now using self-supervised, non-annotated images, text, etc. And then multimodal AI is what we finally get to, the building block for healthcare. Now, this has been incubating for years. I wrote this review back in 2014, and it was talking about all the layers of data that make each of us unique. This is the essence of the concept of individualized medicine. Well, we can gather all this data, but we didn't have a way to integrate it, to process it. And now we finally do, the beginning of it. So it's like all this data that's below the surface that we don't use today, we can't use, we couldn't use, now is a new potential. Now, this is a recent review we had last fall in Nature Medicine about what does multimodal AI do in healthcare. So all the different data inputs from biologic, physiologic with sensors, ambient, environmental sensors, that gives us the capability to do hospital at home, digital twin infrastructure, virtual health assistants, digital clinical trials. It opens up everything, which we couldn't do before. Being able to take data from all these layers in real time and get the important output extraction of information. The hospital at home, Erwin and Paul and I were talking about this over lunch, but this is a reality now. we're going to be able to take patients in their home and have ICU, better than ICU monitoring of today for a fraction of the price, with validated algorithms that patients are safer at home than in the hospital. And one of the examples that could be integrated is real-time wearable continuous ultrasound, a recent breakthrough work from the Jacobs Engineering School here. Extraordinary. No one talks about self-imaging potential. It's a really exciting area. There's already studies being done today where heart failure patients are connecting an ultrasound device to their smartphone and doing cardiac imaging, echocardiograms, without even knowing, except that the heart's on the left side of the chest, and everything else is AI driven as far as acquisition and interpretation. So all these things are part of the hospital at home. Now, you say, well, why do we need a hospital at home? Just look at this. These are 11 hospitals in the Boston vicinity, and there's some pretty high, big name hospitals there included in this. And the average error rate, a breach of safety, was 35 per 100 admissions. 35 per 100 admissions. And what are they? Things like adverse drug effects, surgical procedures, nosocomial infections. Who wants to have any of these and pay $6,000 a night, no less? You think of all the data plans you could have for that much charge in a hospital. For how many years? This is preposterous. This model doesn't work. Okay, so we have been writing reviews about where this field is and where it's going, a series of them in Nature journals, the multimodal AI, self-supervised learning, I mentioned this one, and the most recent that just was in April on large language, Stanford called them foundation models, generative AI. Generative AI is not a very good term because these models don't just generate. They're actually even better at editing and basically raking over a work product than they are even than generating. But what we envisioned in the Nature paper, which came out before GPT-4, was this, that when you have all these trained, pre-training of all these different sources of data, and you have the corpus of the medical literature that's up to date, it's a reset of how we practice medicine for any given patient. And it extends in many different ways, not just for the clinician, but for patients, of course. It empowers patients about their data. Okay, so for example, you're a surgeon and you don't know what you're seeing in the operative field, and you just ask GPT-X, what is this? Help me. And it will give you, it'll guide you through, the surgeon, no less all these other things about even writing apps and code and all sorts of things. So this book is one I highly recommend. It was written by Peter Lee, who is the head of Microsoft Research. I just did a podcast with him, and it's actually really interesting if you're into this, about the book and about the fact that he had 7 months lead time with GPT-4 for medicine specifically. And Isaac Kohani, who is one of the co-authors, who heads up data science at Harvard, he said, and by the way, he's a very conservative physician. He's a pediatric endocrinologist. And he said, how well does the AI perform clinically? And my answer is, I'm stunned to say better than many doctors I've observed. That's a big statement because he wouldn't be one to say that if he didn't. He worked with Peter for 7 months to test drive GPT-4. So I asked GPT-4, what do I think of it? And it told me, actually, it's very accurate. And I even asked it to write did I review the book? And everything is amazingly up to date. It's scary up to date. I even asked it to write a poem about it. It was just, it's pretty amazing. Okay, so, I mean, I am just blown away by this capability. I don't care if it's artificial general intelligence or whatever it is, I really like it, it's fun. Has everybody played with this? And does anybody think it isn't fun at the very least, even if you get fabricated confabulations? It's fun. But this was a wake-up call for me. A patient of mine told me the story about a relative where the patient had seen multiple neurologists, was told, and physicians, was told that she had suffered from long COVID, which I think you all know there's no treatment. But then she put in the symptoms to ChatGPT, and it came back with the diagnosis of limbic encephalitis, which is different than long COVID and has a treatment, which is hyperimmune globulin, and she completely recovered. It's a pretty impressive story. We're using ChatGPT anecdote, but there'll be a lot more of these in the times ahead. Now, what the medical community was impressed with, and I'm not that impressed with it, by the way, but this created lots of interest, was that ChatGPT could pass the US medical licensing exam. Oh my gosh. Well, it's a 60% is the passing threshold. That's not very good. 60%. And by the way, it's not the real exam. It's a simulation of the exam. So ChatGPT got to around 60%, and then MedPalm blew through that at 67%. That's Google's product. Then MedPalm 2 got to 86.5%. And then, of course, GPT had to say, well, we did that already, you didn't give us credit. So the interesting thing is they were rated independently for harm and for quality. And the large language models was far superior to the physician answers to the questions. It's really striking. Then what about radiology? Well, radiology, this is interesting. Just a couple of weeks ago, this group published the fact that ChatGPT did very well on the radiology boards, multiple question boards. And then when they put it to GPT-4, it did even better. And in the passing scores, again, 60%, it got up to 81%. Big differences, by the way, between ChatGPT and GPT-4 consistently across all the different boards. Here's neurosurgery, and they actually found much less hallucinations, interestingly, with GPT-4, which obviously we have a long ways to go to get that problem addressed. Now, just this few days ago, another model was published which exceeded GPT-4 for images, medical images. This is interesting. It was trained in 15 hours. And basically, if you look after patients in the intensive care unit and you ask in the chest x-ray, what am I seeing? The fact that it could detect that there's an endotracheal tube, a central venous catheter, a pulmonary artery catheter, all this stuff is pretty darn amazing, really. So that was a very impressive, another jump when you're having dedicated tweaking for medical knowledge or medical data inputs, which hasn't been the case to date. So there are lots of concerns and what's needed in large language models in medicine. They're summarized here. We have some real opportunities to harness. And I think you're well aware of the concerns like the hallucinations, the issues of data security. I won't go into that, but I will say this paper by the Google researchers that appeared last week about the chasm, I call it a chasm. They didn't use that term in the paper. But there's all these myths that more data is better AI models, only AI experts are needed, all this stuff. I'll refer you to that article in Nature Medicine because there's lots of issues here from having a validated model to implementation in clinical practice, like lack of randomized clinical trials, like a lot of things that are noted here. Particularly, this was about diabetic retinopathy. Google's done extraordinary work on diabetic retinopathy, but when they took it to India, it was a whole different story than the work they had done in the US. Differences in venue, in countries, in patient populations, ancestry, ethnicity, et cetera, have big impact. So this, of course, is the other side of AI and in healthcare, when you start to have inaccurate data and all sorts of problems that you can make things worse. And that's really, I think, very well graphically depicted in this cover at The Economist. and we already have touched on these. One of the things that's a problem you will recognize is when you have to have 20 to 30,000 GPUs, what are academic centers going to do? How are they going to compete on the same footing with the likes of Microsoft and Google and other entities? The tech dominance here is a concern. Yeah, go ahead.
We hear a lot about the cost of GPUs and where they are, but architecturally, in fact, ARM uses GPUs and reduces the size of the processing required significantly. So coming to the academics, it's quite possible that architectural innovations can easily give you anywhere from 100 to 1,000 factor.
Right.
And you're showing
that's what we need desperately.
And you were showing on the last radiological one, 15 hours of training or 13 hours.
Yeah.
So
it's a piggyback though.
Yes.
Onto GPT-4.
So the inference engines can definitely be done at a much lower cost.
Right.
The training could potentially be a IP, and that could be even rented or sold or something.
Right. So this is a really important point that Raj is making. First of all, we have to get this down. That will be doable. But secondly, if you piggyback on top of pre-trained models, OpenAI and others, you don't have this type of extraordinary computing challenge. Absolutely. So you've all heard about the existential threats and why Jeffrey Hinton decided to resign from Google. And a couple of cartoons. Hopefully we're not going to see these cartoons, but I thought just to transition to this last part, I would just show them to you for amusement. Okay. This is my number one objective. It's not about improving accuracy. It's not about multimodal AI. It's about restoring the patient-doctor relationship, which has eroded profoundly over the years. And so if you look at this classic book, Danny Kahneman's book, Thinking Fast and Slow, that is the slow thinking that's reflective, or the fast reflexive thinking, which is what typifies clinical encounters, and all the errors, things that are missed, wrong treatments, ordering too many tests, ordering the wrong medications, the wrong doses, etc. Medicine suffers from fast and shallow. That's what we are today. It needs to go slower and deeper, and we need help to do that. So Danielle Ofri, who's at Bellevue, she had a very, some years ago now, she had a really insightful editorial. She wrote, modern medical practice is a petri dish for medical error, patient harm, and physician burnout, which it is. Doctors hate computers. I should put this in the past tense. They're going to love computers someday. They just don't know it yet, because their first foray into this was electronic health records, which was an abject failure, a fiasco that was destined to be that because it was centered on billing, not on patient care. It didn't give a hoot about patient care, and it still really doesn't today. And so this is the experience as a patient and as a physician today with computers. It isn't good, folks. You don't even see the patient. You're looking at a keyboard, clicking away during an encounter. And this is some of the best data we have about how physicians are consumed by electronic health records, taken over their lives, led to all the burnout and even clinical depression and suicides that are all at the highest levels in the history of the profession. So the idea of virtual scribes, whereby the ambient conversation, whether it be at the bedside or in an office visit, is transcribed into a note. And not just a note, but all the other downstream tasks. And that's being pursued by many different companies. But one that I just, within recent days, agreed to advise is Abridge. Now, Abridge is an interesting company because they're out of UPMC, Pittsburgh, very large health system. And they are next door to Carnegie Mellon, one of the great computer science institutions in the country. What they did is they took every patient from UPMC, put all their records into inputs, and they basically came up with models on top of OpenAI to do all this work, all this administrative work. And they're deployed now, not just at, the first place was University of Kansas Health System, 1,500 physicians, 240 sites. So it not only generates the notes, but it does all the other stuff, pre-authorization, it does follow-up appointments, it does tests that are needed, nudging the patients about whatever the issue was, why they saw the physician, like blood pressure checks and whatnot, prescriptions, whatever, everything. So this is what gives a physician the gift of time. But also, it gives patients more autonomy, that they can just go to GPTX, put in their data and questions, and have a conversation as a front door to the medical world. And so this can really streamline many aspects of medicine. Now, a UCSD paper, which I was really impressed by, was just published a few weeks ago by John Ayers, who you may know, and colleagues here. He isn't here today, is he? Okay. Anyway, they put 200 questions that were already answered on Reddit, which has a medical arm, and Reddit. And they took the same 200 questions and they put them to ChatGPT. And guess what? The quality and the accuracy, as was added subsequently by the senior author, and the empathy were far better by ChatGPT than the physician. And of course, they were much longer responses, as you would imagine. This was covered on the front page of the Union Tribune. I don't know how many of you read the Union Tribune. I do read it every day still. Always learn something in there. And Davey Smith from here, shocked at the level of quality. I was too. I went to the supplementary file. I said, this is really very remarkable. Now, we need a study where the patient goes to their own physician, not just a Reddit doctor, and pairs that with the response of GPT-4, which is much better. But this is an impressive study, and I wrote a whole Substack about it because I think it's really a futuristic and important index study. Now, in that Substack, I asked, this is a shocker to me, I said, can GPT-4 enhance empathy between doctors and patients? And so Bing Creative, which is GPT-4, it answered, and this was the day it was published, it cited that paper, cited the paper that was published that day, right here, today, UCSD. I said, this is amazing. Now remember, ChatGPT was frozen in September 2021. GPT-4 was up to date with the citations. That was just, that itself was striking. The point is that empathy was not anticipated. I didn't anticipate it. I had a whole chapter in deep medicine called Deep Empathy. I didn't think that AI was going to be more empathic. It isn't feeling empathy, but it can promote empathy. It can coach physicians to be more empathic with their communication, which is really something I did not foresee. So I'm just going to leave you with this endocrinologist from UCSF, Aaron Neinstein. And he wrote not long ago, last fall, about how AI has already changed his medical practice as a diabetologist. And he no longer has to futz around looking at all these glucose numbers. Instead, as he says, shed the role of being a poor substitute for a machine and reclaim the role of healer. This is what I hope we'll see someday. So instead of all the hooey about, UCSD, Scripps Health, or whatever health system here that they put on the signs, we give time, the gift of time to patients and clinicians. That would be the way we should be competing. Who gives the most time? That's what's needed. And this is a paper that I think is such a classic from almost 100 years ago now. Francis Peabody, if you read it, you can't help but be inspired. It's 5 pages. The last sentence is, one of the essential qualities of the clinician is interest in humanity, for the secret of the care of the patient is caring for the patient. We don't do enough of that today. So let me just stop there, acknowledge all the great people I get to work with over at Scripps Research Translational Institute, and I'm happy, of course, to answer any questions. Thanks again for having me here today, and congratulations on this really remarkable anniversary and the new building that you're moving into soon. Thank you.
We have time for a few questions.
Well, this is fascinating talk, and in a very classic Eric Topol way, you did show the highlighted articles, which I love. This is not a question, but a comment. We have long felt that for our clinician residents, training in data science is at least as important as public health. So we do have a proposal going through the system on MD/MS degree, and we hope to launch it in a year or so. That will hopefully bring this, bridge this gap, and actually have the physicians be a lot more both precise and accurate at the same time.
Right, right.
So thank you.
No, I applaud that effort. What you've done here to promote this and to keep building on it is just second to none. I think it's fantastic, and hopefully you'll keep that up. Great momentum.
First of all, fascinating talk. Thank you very much.
Thank you.
And you touched on a lot of different topics and how it could be used. And I love the fact that you emphasize giving time back and empathy. One topic you didn't touch on, and I'd like your opinion on this, is how does the insurance company come in? There is a big financial model there and remuneration that dictates the time. How will this help that process, or what role will they play? Are they resisting? Are they coming on board?
Yeah, I think anything that cuts the cost of healthcare, they like it a lot. They like it a lot. So we have emerging opportunities to use things in a much more frugal way, whether it's tests and scans. For example, the recent battle of United trying not to do fund colonoscopies is an example of their interest. Their interest is not in better outcomes. It's only lowering costs, because most of their customers are large employers, right? And they want to do pre-auth as much as possible. So now what you have is a really interesting situation. You have the algorithm of the insurer with the algorithm of the physician going at each other, because up until recent days, it's been physician had to take all this time to try to deal with this pre-authorization process. They're doing everything they can to lower costs, but that's not irrational. That's just basically putting bottlenecks in. But in the future, that is what, interestingly, the major insurers, and I've spoken with United and the Blues in Aetna, CVS, they all want individualized medicine to succeed, because most patients are taking medicines that they don't benefit from. Most people are getting all sorts of scans and procedures, screenings even, that they wouldn't benefit from. So this can all be sharpened. And so for that, they like it. And the ultimate one they like is to not have people in the hospital. And that's foreseeable in the next several years. So yeah, in the background, they're very supportive of this movement, but at the moment, they're doing whatever they can to reduce costs.
So that's actually a perfect segue to what I was going to ask, is almost a little more philosophical. How does all this mesh with the insurance situation, like given the way our healthcare systems work here in the US, if kind of these predictive things can show that I might be susceptible to something, or that I already have something I don't know I have, what are their insurers going to say or do? Potentially, drop me, increase my premiums.
Right.
How does that mesh?
Yeah.
Given the way our healthcare system works.
Right. Well, firstly, let me just say congratulations to you, what you've helped build here. This is phenomenal. So if you look back at that slide or that review we did of multimodal AI, one of the most, to me, the most important, far-reaching, is the virtual health coach.
Absolutely.
So what you have here is all of your data constantly being synthesized along with the medical literature, so that whatever you had a high genetic or otherwise risk of developing in your lifetime, you never manifested that condition. You had a high risk of asthma and you never had a wheeze in your life. Diabetes, you never developed it. That's where we are headed, to fulfill the fantasy of prevention. Now, that will take acceptance by people to have that data inputted and fed back and coached, okay? There's actually a chapter in the GPT-4 book I mentioned about this virtual health assistant in the primitive form. We are headed there now. We have a way to get there. It has to be all proven now. Between now and then, your concerns are very legitimate, and also not a lot of people who don't want to do this because of issues of privacy and security. But those of you who follow this field realize that one of the real exciting parts of AI is privacy computing. And that hopefully is going to reduce the levels of serious concern. But I think this is a fast forward, you can see your way through, but I share the concerns you raised. The problem we have today is I could tell you the risks that you have, that we all have for all the common conditions, from a low pass sequencing or even a 23andMe, polygenic risk score for every type of cancer, for diabetes, for inflammatory bowel disease, atrial fibrillation, you name it, heart disease, but we don't use the data we have. And we have a paternalistic research community who says, oh no, if the person gets this data, it's going to give them anxiety. Whereas if they had the data, that's their first step to actually do something about it. And the problem in the medical community is it has this inherent belief that patients can't handle the truth. And someday, they will have the truth because they'll get it directly. They'll bypass it because this paternalism can't go on. But this is the problem. There's a lot of risk we can give patients assessment today, which we're not using it. And we will eventually. It's going to be inevitable. Okay.
Eric, I have a near-term question. One of the databases that's important and have been important in my life is ClinVar.
Yeah.
And people have estimated that maybe 10 or 20%, at one time it was around 20%, I think it's lower now, of the information in ClinVar is wrong.
Right.
Either the sequence is wrong or the association is wrong. The work of pathologists, there have been studies of pathology diagnosis, incredibly high rates of, disagreements and probably error. So with all these databases that the AI is drawing upon, having these high error rates, what's the near-term impact of that? And are we going to have a fair amount of misdiagnosis by the AI generative faculties as we have with the human-driven one?
Yeah, so this is an important question because if you go back in any of these resources, they're error-laden. So the sequence of the genome in 2000, 2003 had so many flaws, it's incredible. And even the most recent build in 2017 was just full of errors and incomplete. So the pan-genome, which was first published a few weeks ago in Nature, with 47 instead of one person in Buffalo, 47 diverse ancestry, it's going to be 350 by the end of or middle of next year. That will correct our understanding of the human genome to a large degree. ClinVar is yet another resource that's going through a continuous quality improvement. It will get there. It's much less than what you cited, but it's still on its way towards an error rate that is, much, much lower than it is what would be acceptable. Zero is what we want. We'll never get to zero. But I think the other thing you're bringing up is when you do a prompt to a GPT-X and you are suspicious that there's something wrong here. Now that's where there's an advantage of people in the medical and life science space. This doesn't seem right. What's really interesting is you just do it again and again. If you do it like triple data entry, you'll eventually get the right answer, interestingly. And then you can confront the first GPT and say, actually, you're wrong. And the GPT will apologize. Say, I'm very sorry, you're right. So there is, interestingly, a thread to get to, particularly when you suspect that you're getting something wrong. So if you're seeing some kind of mutation say, that doesn't seem right. If you just go at it a couple more times, you usually get the right answer today. And that's with models that were not specifically medically trained, which is incredible to me, right? I mean, that's one of the things that's so striking is all the stuff that we're seeing with open source, non-medical, special input.
Hi, Eric. Really enjoyed your talk. I just had a quick question because I know one of the things that's like been kind of plaguing the medical industry as of late has been like the idea of like the, the very much white male kind of default as to a lot of the diagnoses and the treatments that we give to people in like the healthcare industry. So my question is, because of like bigger models such as like GPT-4, and it's harder to unbias those kinds of models, how are we going to address kind of the systematic inequalities that exist for like minorities in healthcare, and like how can we kind of transform AI so that it becomes more?
This is a very formidable challenge. It's not the fault of the AI per se, it's the fault of basically our culture and embedded biases. We've learned, and like what Paul brought up, in genomics, which we started out, it was all European ancestry, and it took too many years to figure out you've got to get all ancestries and ethnicities, indigenous people, you have to get that represented. We have to do oversampling for AI inputs to try to neutralize these deep biases. And there's no question about them. So this is a problem that's not only was bad in the deep learning era, but in the transformer era, it's likely to be worse. So we have to work on this. And I agree, that's a fundamental issue that could hold us back. Yeah, sure.
All right, I think we should wind up here, and we'll take a short break and set up for the fireside chat. So let's thank Dr. Topol again for a wonderful talk. Okay, sorry to bother, but I'm going to ask you to take a seat again, please. Please have a seat, everyone.
I had to learn how to pronounce that because I had a colleague who was a German logician at Carnegie Mellon.
So David, sorry to interrupt. I'm going to start now. We can start, right?
Yeah, we can start whenever you
I'll
want.
just introduce you, and then you can introduce all the panelists. Okay, wonderful. All right, let's get started. I'll invite Professor David Danks, a professor of philosophy in HDSI, to introduce our panel and to lay out the rules for the game. Thank you.
Thanks so much, Vineet, and thank you everyone for being here on this wonderful day. I kept thinking the sun was going to peek out at some point for the people out on the patio, but it looks like not quite yet. So it's my real honor to get to moderate this panel, looking at the intersection between and interactions between academia and industry, because that's such an important part from the very beginning of how we've thought about, I've been here only 2 years, but we've thought about the role of HDSI, both intellectually and within the university, serving to help bridge the ways in which data science is influencing our lives outside of the campus, while also serving the students, research, faculty, postdocs within the campus. And so when we think of HDSI as this bridge, both internal, from the internal to the external, from the university perspective, it's critical that we connect with industry, because the reality is that these days, some of the most exciting and important work in data science is occurring in industrial settings. It's occurring in both the large tech companies, your Googles, your Intels, your Deloittes, but also in the small startups that are just across the 5 here in La Jolla. And so the Industry Liaison Program has been a critical part of HDSI since its founding, and we're delighted to have 2 longtime partners of HDSI here, as well as 2 of the faculty of HDSI. So without further adu, to my immediate left is Bijan Arbab, who completed a PhD in computer science and mathematics, actually with Alonzo Church. He were just telling me that he was Church's last PhD student, and if you've ever taken logic, you'll be really excited about that. If you haven't, you'll wonder why I'm so excited about Alonzo Church. He started his career working in programming languages and networking research and development, and created and then sold an IP telephony company, Joined Dialogic. Did I get that right, approximately? And which was purchased by Intel. He is now a director of system telemetry at Intel, and perhaps far more importantly, is an HDSI fellow. Ilkay Altintas, I'm sorry, I always getting better each time, is the Chief Data Science Officer at the San Diego Supercomputing Center, and similarly, more importantly, is a faculty fellow of HDSI. Her research focuses on workflows, systems for application of large-scale cyber infrastructure and data to scientific and societal problems. So for example, issues of wildfire prediction here in California. How do we use the large computing resources effectively to do that? Thank you, okay. Rasmus Nielsen is a senior manager and specialist leader at Deloitte. He has a background in economics, finance, banking, and capital markets, focused on financial risk management. And within that context, he works with ethical AI and on bringing AI risk management tools and practices to US government agencies. I should also make sure to note that Rasmus was a mentor for 2 undergraduate capstone teams this past year. Rasmus and his Deloitte team. I was lucky enough to get to be a fly on the wall as those capstone teams did their work on trustworthy and responsible AI development. And finally, but not least, of course, Ben Smar, who is an assistant professor of bioengineering and data science. And he studies biological rhythms, leveraging them to increase precision in biomedical applications. His lab uses data science techniques to make dynamical models of human physiology and behavior. So it's a somewhat eclectic group that we have up here, but all people who have been very active at this intersection of industry and academia. So I want to start with perhaps the positive side of it, and I'll start here with you, Bijan. You have a mic there. What has been the most rewarding part for you of working with academics, with Ilkay, Ben, myself, others?
Well, it's really been people and purpose. Smart people gather in different places, and both in administration and in faculty. And what's been really unique and rewarding here is that to see and experience the purpose of everyone and coming together and really focusing on the students, of whom I'm very jealous. The focus is not just doing good research, collaborating with universities and bringing the students along, and the spirals, the successful spiral that has been generated by that. We've been a beneficiary of that, hired a number of students there, have had the pleasure of doing now 15 different studies in addition to 3 years of capstones, which has benefited us and resulted in us identifying new things we didn't know we had over the past 3 years. It's been very rewarding, and again, it comes back to what Rajesh always says, it's people and purpose.
So Ilkay, you get to not just sit in between industry and academia, but also the SDSC. And so you've been sort of at this nexus of people and purpose that I think that Bijan's referring to for more than just the 5 years of HDSI. For you, what is the most rewarding part about being able to sit sort of in that intersection?
Yeah, I think it's the convergence of the minds. When you think of the problems today in science society, they are relatively complex. And when you tackle complex problems, you need everyone's frame of view. And especially in these collaborative public-private partnerships or that involves cross-sector, not just academia and industry, but also nonprofits and government sector. We need to have a way of working together so we can actually bring those innovations really forward. Now, we've seen anything from working in talent development in this space, but also translation of something that comes from research to scalable use through industry processes and types of agreements that would be required for bringing it one step forward. And of course, coming from SDSC, working with industry from a scalable systems perspective is also really attractive because it's not just one system, but there are many systems, and bringing them together, both from performance and data science points of view, so that we can be the neutral place, so to say, to work with these advanced technologies and see how they could be beneficial in support of applications and research has been another avenue that we followed.
Fantastic. Rasmus, I'm going to sort of put you on the spot here because you're maybe the newcomer of this group because your team only came connected with HDSI in the last year or so.
Yes.
For you, what have you found most rewarding?
So we've been part of this 1 year, and first I wanted to thank you for inviting me today. It's really excited today. I've been here the whole day this year. And overall, or first, we all had a great experience teaming with you, working with you, and working with the students who were really generally excited about this topic of responsible AI that we're working on. We enjoyed this, saw it as an opportunity to create more awareness around responsible AI. That's what we're working on, and hopefully inspire, motivate more people into move in that direction, maybe pursue a career within ethical AI. So what we did, our focus was on introducing practical challenges as we see them in the industry, to try to bridge the theory with the practical challenge that we experience in our daily communication with the clients. And in that way, maybe help the students smoothen the transition from when they move from academia into practice. To us, it was just great to see how enthusiastic the students were in terms of their ability to acquire new information, adopt new ideas and theories, and take ownership of those ideas, what they've learned, that newly acquired knowledge, and apply that to their projects. That were really great to see. And in totality, teaching like this is highly relevant for what we do when we go and talk to clients. But in an area like responsible AI, it's new. It's growing a lot, but it's still relatively new, and there are not that many people around that do it. So when we go and face clients, we usually have just basic conversation about what is responsible AI, why is that important, why should you do it, what can we do for you, how do we do it, all those basic questions. And that was in the same way what we did in this curriculum. So it was interesting for us to have that same level of tone and conversation that could help us when we meet clients.
Yeah, it's interesting to think about the overlaps between teaching students and having to teach your clients. That in this area of ethical and responsible AI, many of your clients, I'm sure, they don't even know what that means, and so you're having to step forward and help explain it.
Exactly, I get a lot of unexpected counter questions for what I think is obvious, but it turns out not to be obvious. But that just illustrates that we have a long way ahead of us in terms of responsible AI, as Professor Topol talked about before. But yeah, I think this is definitely important step in that direction for us. So thanks.
Wonderful. Ben, I'll look to you now. What have you found to be the most rewarding aspect? I know you've done quite a bit of interaction with industry from your academic position, including with Intel and telemetry data. So what do you find to be the most rewarding aspect of that?
Yeah, I think that in the short run, it's very rewarding to see the students get this kind of exposure, right? That I'm an academic, I like being an academic. Most individuals in the world are not academics, right? So most of these students, they're going to do something else. Helping them see that the skills they're learning plug in the real world feels good, right? You see them get sort of lit up by that, I think. In the longer run, it also gives me a hope for the kinds of good things that come out of these collaborations. So in those instances when companies are able to share data, which is how a lot of my research has been done, we're able to find new things as academics that, they're not the quarter-to-quarter priority for a company, but they end up having a much bigger impact as long as you can invest in that longer horizon. And so having the students that then go to work in these companies with that mindset, I think gives me hope for the future that we can have cultures that allow more of that kind of collaboration, right? That ends up being a much nicer way to sort of grow the pie, as it were, globally.
So I want to pick up on something you said there and actually pitch it over to Ilkay, because you used the word translation. You talked about the different time horizons that a company versus an academic might have. And I think there is this kind of caricature that academics, we care about advancing the frontiers of knowledge and teaching the next generation. Companies care about money. And that's it, right? And so these seem to be incredible, almost cross purposes, because the things that advance the frontier of knowledge, we have no idea how those might possibly result in profit. Now, just to be clear, I think these are caricatures of both sides, but I'm curious, you use the word translation, and that seems really critical. And I'm wondering, Ilkay, whether you could say a bit more about the ways in which we could do translation. The US government, National Science Foundation now has the Technology Innovation and Partnerships TIP Directorate, which is supposed to help with some of that translation. And I know you've been very involved in those efforts, but maybe you could talk a bit about the translation from academia into industry.
I think it goes back to the innovation thinking. There's a process from research to industry and translation of that research into some scalable use. And right now in the US, of course, translational computer science and translational data science are becoming buzzwords. What it means is actually taking the findings from research and applying to an area of industry that could be turned into not just industry, but a solution that could be co-developed and given to the hands of the users. To go from the research or data, in our case, to the user's hands, there needs to be a number of things that goes right. So one, of course, we start exploring with data in these capstone projects or research that's in the lab, and that leads to sometimes disciplinary, sometimes multidisciplinary work. And it creates this understanding of what can be done. So we've used data, Ben and I, in many capstone projects over the years from different industry, actually, providers. And that's real world data that needs to be cleaned up, and we explore with it, with the students, with the faculty members, and that creates the state of the possible, the understanding. Going from that to add some more research to it, so it's through some co-design partners, which now the TIP Directorate and NSF refers to as the convergence research. That's actually going from that lab thinking to something at the societal scale. So convergence research is still research. You're actually coming up with a solution to a problem that's very use-inspired. So at the end of it, you have a solution, almost like a prototype of a product that could be given to the users. So that creates this opportunity. But how are you going to take that opportunity and make it scalable for use? So what NSF TIP Directorate also noticed that this best happens through the partnership of different types at the cross-sector. So at the minimum, a research and academic partner together with an industry partner. So that involves some tech transfer and some form of translation of the research product into the societal or industrial scale applications. So I think that process is now slowly emerging as an evaluation model, and NSF, the National Science Foundation, now adding technology to its portfolio through this TIP Directorate. Technology innovation partnerships. And I think that's going to be the next 10 years. We'll all see what will come out of this new directorate and programs. Very exciting.
Yeah, I mean, the federal government getting directly in the business of helping to almost matchmake between academics and industry. And I guess, Bijan, I want to ask you sort of the other direction, though, of the transfer. So Ilkay talked about the transfer of basic research into into industry. But I think one of the things you've really brought as a fellow, as an industry fellow to HDSI, is the other direction, taking industry problems and being able to bring them back to be the kind of basic foundational research that we specialize in at HDSI. So could you talk about the opportunities that you've had, that you've been able to bring, but also perhaps even some of the challenges of bringing industry ideas and problems into the academic research enterprise?
Absolutely. Thanks for the question. I find in life, questions are more important than answers. What questions are you going to address your time, resource, energy to? What's worthy of it? Because, money, funding, problems of somebody, I think you said characterize, industry is all about money and caricature. Yeah, you can have lots of money, but time is something that never comes back. So what problem are you going to address your time to? And identifying that is very important. That's what this environment is about. And that's what something that sometimes in the industry, because you're so focused on certain tasks, you don't get the chance to have peripheral vision or look around. And this is what this environment has brought up. We start in our engagement, with Ben. We started with Eric almost 4 years ago, 2019. We dedicate ourselves to 5 problems that are of interest to people, to some number of professors and some number of Intel fellows, Intel senior principal engineers or engineers. They identify the problem. They have an issue. They bring it on. And then you form passion around it because somebody says, "Oh, that's a fantastic application of time series," or I've been working on this algorithm and I can maybe, then we can come up with the answer. And we dedicate 9 months to coming up with an answer. That's what's been great about this application, or this type of an environment, people on purpose. And students get excited by that. I'm amazed of how much time an undergraduate student puts in, and I was in hiring positions, and I would never look at an undergraduate student, which was the wrong thing to do, because hey, I wanted somebody in a master's and a PhD program, but found out that it really doesn't matter. It's the work that they do and the passion that they put in. So very unique environment here.
Well, I think one of the key things you were saying there is that it's not about Intel coming saying, "Here's this problem, somebody go solve it for us." It's about, here's this opportunity, and where do we find sort of a shared passion, a shared energy?
Absolutely, yeah. And that's been critical, because unless the professors that are coming up, the professors are not dedicated or getting a paycheck from Intel. So why would they be interested? Because they're interested in addressing the question, the problem. Yeah.
Yeah, it's fantastic. So Ben, you get the perhaps unwelcome task, but I'm going to pitch it to you anyway, of maybe starting to talk a little bit about what we could think of as the sort of darker side of the collaboration, the challenges that might arise. We're already sort of seeing opportunities. We've been very positive, but could you say a little bit about, for example, what is, I'll say it this way, what for you has been the hardest part about working with folks in industry?
Yeah, working with people like Bijan is a great pleasure. And so exactly what he said, I think, is the response to that caricature, right? It is true that companies generally say much more aggressively than Rajesh would ever say to me, how much money have you brought in next quarter, right? Some.
Just wait. Once you get tenure, all gloves are off,
But Bijan is a person and I'm a person, and we're not companies in academia. And so if we both go, hey, there's this interesting thing, I think I see some ways this could help the world, be useful, be valuable, and then we get to have these conversations of, this, I won't call it a darker side, but just sort of the reality constraints of like, okay, I do want to share data. I do agree this is an interesting problem. I do want to dedicate several years of a student's life to focusing on this and not something else. How are we going to make that happen? How are we going to convince other people that there's, from the point of view of federal funding for me, that this is one of the things they should focus on, given that they could be focusing on a gajillion other things having to do with health that are more real, that are more conservative, right? I'm not doing the next obvious step in cancer treatment. I'm trying weird things about new forms of data that might help us understand cancer risk in some totally other way. Maybe that's a gamble, maybe that's not how we spend taxpayer money. Bijan maybe is doing a similar but different dance saying, look, this is not going to be the next Intel processor, but this is going to surface a bunch of value in data that we have. You shouldn't kill it, right? So there are these very different real world constraints. The flip of that is, of course, we then educate each other and we figure out how do we reach broader perspectives, different perspectives than just my audience, just his audience? Does that really make a stronger argument? Does that really help us surface better things? So that's a challenge, but everything has challenges. I think it's probably healthy for me to not just think everyone around me is academic, so that's how the world is.
Wait, not everyone's an academic? That's so weird. So Rasmus, I want to pitch in some sense, the reverse question to you, because, especially, Bijan's been hanging around HDSI for quite a while. He's used to our weirdness. But for you and the Deloitte team, who have really, just in the last year, been connecting with HDSI, and we hope it's the beginning of a very long friendship, but what have you found to be challenging about coming to work with an academic group? What have been the hard things about building this collaboration with academics?
I mean, seen from a more like practical perspective, we're not all academics at Deloitte, so which means just it's a very practical level. It has been a little time consuming for us to take time out of the calendar to build the curriculum and the materials, but okay, it's just a one-time cost. It's easier in the future. So, but I think the communication has been a little difficult for us as well because it's remote. That's how it is. And we're located, most of us, in DC, so we're not around the corner. It could have been helpful if we had more direct one-to-one exposure with the students to interact. That's not an easy problem to solve, I know that. But I think those are some of the key points we brought with us in our evaluation process.
Yeah, I think that the issues of communication raise a really valuable observation about, I think, often a challenge of industry-academic collaboration. As much as we've all gotten used to being on Zoom, there's no substitute for, well, I guess Ben's over in Franklin Antonio Hall, so I have to walk, across the quad to go talk to Ben, that if we want to build a research collaboration, or if we were to co-teach, it's easy, because I can just go and just knock on a door, and those, we can do remote interactions, but we need to find a way to get you out here more.
Yeah, because like curriculum is not it's not a monologue, it's a dialogue where they interact. So it's not just one person, delivering a speech. So we're missing out on that dialogue, but okay, that's the new normal. We'll have to accept.
So while you have the mic, I want to ask a question for you, which is building off of these ideas of translation. So shifting a little bit away from the educational side. When you look at your work in ethical and responsible AI, especially as it connects with the US government and so on, are there things that you wish we academics were researching? Are there things that you wish we could bring to the table as you're trying to help ensure that the federal government is using AI that truly benefits all of us rather than just the select few? Are there translational opportunities perhaps there, if only we academics could settle on good questions?
Yeah, that's a great question. So what I do most is to be that bridge between academics and practical work for our clients. And what I see a lot is that clients are typically not ready at the same way that we are to buy ethical AI as a product from us. So everybody has some kind of knowledge what it is, has heard about it. They know it's important, something needs to get done at some point. They know exactly what it is and how they do it. They just know that at some point in the future they'll do it. So there is no urgency to it. So there is no push, there's no regulation as of right now. So why pull a lot of money out of your budget to pay a firm a couple of $1 million, whatever it is, for something you're not actually required to do right now? I do my best for existing clients to pitch new ideas, and there's certain willingness to be receptive, but just not at the level that academics has the ability to bring it to as of right now. And I hope and I believe that going forward, we're going to have this regulatory push at some point, maybe, triggered by some major events, adverse events, something like that. That's going to push that agenda, which will close the gap between industry and academics.
Yeah, or maybe some academics, some smart economists could show that there's a positive return on investment for it. In which case, suddenly they'd be a lot more interested in it, I imagine.
Exactly.
So Ilkay, you haven't mentioned that you also have been incredibly active in the Master of Applied Science in Data Science, which is geared towards, as well as our online Masters of Data Science, both of which are very much geared towards people in industry who are are upskilling or transitioning into a different industry, or just generally trying to build their value for their company and their organization. So how do you bring insights from academia to students who are coming from industry and vice versa?
That's a great program, because I think right now a lot of industry careers are being transformed with data science. So we have a good student base there who are interested in data science and who's been VPs and all career ranks in different companies. And it's a challenge because we'd like to definitely give them a strong data science foundation, but also we need to be respectful of where they are coming from and make it a little bit more practical. So it's a balancing act, because through theoretical foundations that last, they'll actually be able to build on what we can provide here. So that's been, in that sense, both practical, but through still very rigorous theoretical settings, so that we can balance what they're learning and what they need to learn in the future. And a big part of that program is the capstone course. Actually, that's a real-life project that goes from messy data to a product. So it doesn't just end in analysis of the data, but we try to give them also this thinking of, how do you actually solve a problem? What problem are you solving using this data? What are your data pipelines? How are you applying data science to those problems for what users? And how does that product of that data science ends in a product that those users can use? So it's a full-blown process of going from data to users who can take advantage of products of that data. And within that, I think a lot of things come up, actually, because we have both academic and industry partners with different problems that they come to us. And one of the ground rules is mutual respect, like any collaboration. And we don't refer to our industry partners as clients, but we refer to them as partners or collaborators. And also, on the other side, I need to talk to our partners from the beginning that this is not a consulting resource. Students aren't consultants, and they are here to be trained in a certain area. So they need to be actually approached from that perspective and given enough freedom to develop themselves and develop the skills they need to have going forward. And the other part of that program is actually our students are actively at times trying to change careers. There's a reason they came to a professional master's degree on top of their daily work, because this is a program that our students come every other Saturday, Friday and Saturday. So it's like an executive MBA, it's an industrial master's program, professional master's program. And in there, I think there is this continuous mentoring that bridges what they can do with what they learned here and what could be the next step for them. So we do quite a bit of mentoring and at times actually link our students to our industry contacts and have them talk to them. So I think everything we are doing is talent development, but when your students are professionals, on top of that, there's a little bit of a career development that needs to be together with that, apart from the universities of core resources for career services. So there's a lot of faculty mentoring, and I really appreciate all my colleagues' work on the coffee chats and everything else involved.
Yeah, and I think when you think about that kind of mentorship and career development, it of course also extends to the students in the residential graduate programs. And Ben, you actually in part inspired by some feedback we got from industry partners, created a new course, Soft Skills for Hard Science. Is that what it's called?
Something like that.
Something like that. And I was hoping you could talk a little bit about that course and how was that informed by the feedback that you and others of us got from the industry partners about what they wanted our graduates to be able to do beyond the math, beyond the coding.
Sure, yeah, I'd love to. So sitting on these board meetings, listening to feedback, the feedback we tended to get was, well, your students are extremely technically skilled, there's no question there. Sometimes they have trouble explaining themselves to clients, or they can't explain themselves to the manager, why did they choose this analysis? Can you help warm up those skills, right? It's not enough to just have the right tool. You need to know how to trust it, how to apply it, how to help others see that. And I've done a bunch of like K through 12 outreach for neuroscience and science and data science over the years. So I'm far from a professional communicator, but I like this kind of a thing, and I feel like I had relevant experience. So I was willing to take that on. Students seem to get a lot out of it. They get a lot of exposure to, I mean, you've visited, they get a lot of exposure, you've visited. You will maybe.
Rasmus here on tap.
But giving exposure to students in 20, 30-minute sessions of, from the real world, why would you care? How do you see these problems, data science problems, communication problems, management problems? And then there's just a lot of exposure, writing, short form communication, oral presentations, data visualization. And the students universally like this. The last time I taught it, there was 100% approvals, and the students say things like, this is great. I really hadn't appreciated how to make all these skills relevant, or I feel like I have this much bigger impact now when I'm talking to my groups in other classes. We are all people, to go back to a theme there, right? We need these data science in the world. That means as people, we need to see how it roots into the world and help others see that.
Rasmus, I saw you nodding along when I was describing that.
Yeah, a little bit. No, it's just that reminds me of that. That's like an ongoing work, even for people who've been several years in the profession. That's great technical skills, many cases, but the story is lacking. So that's a common feedback I gave. Like, okay, you've done a great analysis. Okay, then you need to put it up in a way that people can understand it, is in some kind of format. And then thirdly, you need to provide the narrative. What are you doing? What are you doing here? What are we trying to say by doing this analysis? And those are the last two steps that I said there, presentation and building a narrative. That's the part that's very often, I wouldn't say always, but close to always lacking when you get like the more junior data scientists to work with.
And I'd imagine some senior data scientists as well.
Certainly, yeah.
Yeah, just since you say that, it is the last two, it's sort of putting the polish on the thing, but part of what we also have been trying to teach is the executive function, right? Why would you even start on this problem instead of this other problem? And that is one of the things that I hope we have a positive influence through these collaborations, is the students go into industry not just to be communicative, skilled labor, but also thought leaders, right? Also really saying, hey, there's this opportunity space that might not be obvious.
Well, the problems that people tackle, the narrative, as you said, Rasmus, it seems to me that all comes back to the purpose that you were saying, Bijan, and finding that shared purpose and being able to communicate that purpose to a manager, to a professor, to a client, whomever it may be. And when we find that shared purpose, though, a concern that I think could come up is, suppose you and I do great research, we produce something amazing, we find some great insights. Who owns those? So how do we handle, because I know some faculty get very nervous about engaging with industry because they worry about IP, they worry about the intellectual property, they worry about having to sign an NDA to see the data, or how do I control the data? How have you, in your sort of bridge role between Intel and HDSI, how have you worked to try to overcome either the actual practical issues, but also the perception of these kinds of issues that I think can persist in a lot of people's minds?
Absolutely. Well, my father is probably going to roll in his grave because I'm going to quote him. He used to tell me all the time, upfront war is better than back-end peace. Of course, he always used to tell me, you never listen to anything I say. So now that I'm quoting him, he's probably rolling in his grave. Together with Eric, Sophia, and the rest, and Rajesh, that was the problem we took on. And you know, we no shortage of legal. We had lawyers on UCSD side, and we had lawyers on Intel side. There is no shortage of that. And we spent about a quarter, which absolutely amazed me because I thought this was going to take at least 6 months to a year. But within a quarter, we addressed both publication and IP issues and how we set a framework on how we would address those problems. We cannot solve those problems ahead of time. But if we come to an agreement on how to address those things and talk about concerns, then we can solve that. And using not legal language, but very plain language, we put some things up front. What's the industry fear? Hey, please don't embarrass us. What's the academic fear? Don't you dare tell me what I can publish and not publish. I'm here because I want to publish the work. What do you mean you're going to have control over my publication? Well, we don't want control over your publication. We just don't want to be embarrassed. Can you understand that? Yeah, sure. Okay. So now we have a common ground to address it. IP. Was it my idea? Was it the other idea? Can we agree that we were in the room and had a non-zero contribution towards this? And I tell you what, Rajesh, you tell me what percentage contribution I had, as opposed to me saying it was 60%, and you saying it was no more than 40%. Okay, but if we can come to that type of agreement and have that kind of upfront discussion about that, then it's easy. I know we have a legal agreement. I won't be able to cite it, but I know for a fact those were the guiding principles, the guardrails around which a very dedicated lawyers, one of the lawyers on UCSD side, called me from the delivery room where his wife was. I'm like, what are you doing calling me at this time? But that's how we got it done within a quarter. Being upfront about the issues and fears on both sides and being able to address them.
And it's held up?
For 4 years now.
Wonderful, wonderful. So Ilkay, when we think about these issues of putting things out into the public, whether it's through these industry partnerships, your own work looking at how we can produce systems that provide societal benefit, how do we think about what our responsibility is as academics, say, or as people engaged in translation? Our responsibility once things are perhaps out of our hands. We're contributing to this, and I think that's another reason that people are sometimes a little shy about industry collaborations is, I might do this work, and then who knows what somebody's going to do with my idea? They might use it in ways I don't approve of, but of course it's out of your hands at that point. So How do you think through some of these? How have you worked through some of these kinds of questions?
That's a real fear for anyone working. So we need to definitely be cognizant of the fear in the first place, and think of why the fear exists. It's almost like from a researcher's point of view, you have a baby and you give it to a nanny and you won't see it ever again, kind of thing. So they can grow up to be something that you never intended for them to be. So I think a way to really think through that is what Bijan said. There is a purpose for a product to go out there. And the product that we are actually engaging to sort of translate needs to have a model of use that we all agree, and some gaps that are identified in terms of where it does not scale to. So this is really the transferability of the solution. And there needs to be some agreements on how, we need some hands-on approach in that sense. We call that the period, the co-design and co-development period. So that needs to be figured out through a partnership model. So just because something can see the light of day doesn't mean it should in the first place. So going from a prototype to a scalable use, we need to identify, first of all, is that a responsible thing to do across the board? Or does that scale to only one type of problem? And what is it potentially hurting in the long term? And without that proper analysis, I think, and a model that we can legally agree to, it's really going to remain a fear, right? And it's hopefully, once those are solved, there are other things, of course, around it in terms of responsible use of technology and science. I think we can be a little bit less fearful of it. And also, the more we can remove these barriers early on and lower them at least as a culture, and I think that's something that's happening through these collaborations and early agreements at HDSI, we can see faster progress. Right now, the cycle of science to policy is about 10 years. And in COVID, we needed those faster. So some of those solutions were 2 years because, there was a real need. But I think even in terms of issues of privacy and things like that, everyone's now, okay, we are out of that period. What did we learn from this? How can we step back and see what would we have done better to prepare for it, rather than, have the crisis and push all the boundaries and risk some things so that we can arrive at those solutions. I think it's same for this type of cross-sector collaborations. When we say academia and industry, it's a part of it, right? There's all kinds of sectors in there that we need to think through and create those collaboration models. Once we start thinking of how do we create an environment through data, that data becomes a currency for collaboration, and we have a responsible legal and collaboration framework that we could actually work together in. I think that fear is going to get less and less, and we'll be able to arrive at effective, faster transitions.
I think one of the things you said there is really important, which is that, in fact, having that fear and so putting up the barrier to conversations with industry actually can make it even more likely that things are used in ways you didn't intend, because it seems to it sort of plays into this stereotype that these are two different worlds, as opposed to understanding that real collaboration, the academic can have significant influence on what happens.
That's actually a super important thing that Bijan said, is this bidirectionality of it. The university model up till now is tech transfer, like innovation happens here and it gets transferred, or science happens here and it gets transferred. And I think we are moving away from that world, that there are real life problems with people who need the solutions, and there's both industry and academia contributing in partnership models that are actually helping to solve those problems faster. And in that communication, we really are learning from each other and creating an environment and space for everyone to work in. I think as a university, that type of culture needs to be built. And thanks to Eric's efforts and all of our faculty, I think we built some of that culture from the get-go. And that coupled to things like Data Science Alliance and nonprofits in this space, I think it's a whole ecosystem. I hate that word, but that's, I think, fits here. That is required for it. So it's not two people getting together and collaborating. It's the whole organic setting that it happens in.
Yeah, well, and I think one thing, when you talk about the ecosystem, we've obviously focused here. We have representatives from two, shall we say, not small companies. I don't know the numbers exactly at Intel and Deloitte, but I imagine they are at least in the tens of thousands of people, if not significantly higher than that. But Ben, I know you've collaborated with 5-person startups. So you've collaborated with Intel, you've collaborated with tiny startups. Are there differences between those? Because of course, the startup in technology, in tech, the startup ecosystem is itself an incredibly powerful engine for innovation and change. And folks like Taner and others have been working very hard to build that ecosystem here in San Diego. So in your interactions, what are some of the differences between startup and, shall we say, not so startup, more established companies?
Sure. I mean, I think startups, there's a lot more enthusiasm about potential, right? There's less to lose. And so there's a lot more saying, well, let's take risks and do things that might be innovative, that might differentiate us. That's, I think, to Ilkay's point, a great place for these collaborations, because the value that I've added to some of these groups is to say, that's a cool idea, but there are some real hurdles to that actually working, right? Let's think about, so an example is during 2020, a company approached me and said, if we had built a wearable that we could put onto employees that are going into every store basically, we could tell if they're getting sick in the morning, and then we could make sure they don't get their customers sick that day, right? And wouldn't that be an amazing business? And you go, well, yeah, that would be really cool. There's a lot of biases in how this works. You're probably just going to end up telling a lot of disadvantaged people that they also don't get to go to work today, and it's going to come out years later that this was not preventing COVID spread. It was just sort of unfairly biasing who you were saying looked like to the point we talked about with Dr. Topol, right? White males were going to be told they could work a lot more than everyone else under that model, probably, right? And so, they weren't like weird and malicious about it. They had a good idea, they were excited, and they were very open to that kind of direction change, right? And so I think that's the most fun time, right? So the opposite side is people like Bijan come out of these larger companies and say, I've sort of carved out a space wherein we can be, once again, a little bit more creative and risk-taking. But, just like me being an academic, like I have all of this paperwork to go through every time I want to start one of these relationships. If I was just being me, I wouldn't have all of that, right? So scale brings resources, brings collaborators, brings a certain amount of red tape, as we all know. I think startups, it's very similar. When they're young, they're much more flexible. Hopefully they're educable. And then together we come up with what's maybe a more reasonable and realistic target that they can then go run at. That's very satisfying.
Yeah, and I guess here I also want to now turn to Rasmus and say, we talked about startups on the small side. There's another very large actor in all of this that you interact with on a daily basis, namely the US government. And so when we think about these kinds of industry academic collaborations, what do you think might be, as somebody who spends a lot of time in that world, what might be the role of US government? I'm not putting you on the spot and asking you to declare policy preferences or anything like that. But how should we think about the US government? I mean, Ilkay mentioned NSF and the funding role in the form of TIP, but what other kinds of opportunities might arise by thinking about government, especially the US government, federal government, as a player in this ecosystem as well?
Right. So I think what they're asking depends a lot from the specific use case. So I see intelligence community is about safety, health. It's all about not all about. It's a lot about privacy, PHI. Work for someone like HOTS, GNMA, it's more like financial services. So it's fairness, explainability, how well do they understand this? But I think they generally understand well what the problem is and also what the solution is, but because we do have the solutions from academia and as well as for our experiences with other types of risk management from for example, from financial services, where that has been applied for the last, very successfully for the last 15 years. So capabilities are there, the motivation is there, at least in spirit. In action, not so much, yes, but that's what we keep on pushing for, showing the capabilities, developing POCs, proof of concepts, that's showing we can do this and that for you. You may not see the ROI right now, but this is where things are heading. And you need small versus big firm. Small firms have, in many cases, they're designed for a specific purpose, so they have a certain agility that big firms don't have. But then big firms have the many years of experience, for example, within risk management, of anything about data-related risk management. We've done that for many, many years. So there's some things to build upon. The capabilities are there. We just need to go to that next step where we actually execute on it.
Yeah, no, it's really helpful to sort of think about, we've got the title of this session is about industry and academic, and of course industry is many, many different types of industry. Academia is many, many different types of academia. We've got research collaborations, we have educational collaborations, we have service and outreach collaborations occurring as well. And then, of course, there are all of these other actors in the tech and data science ecosystem that we did not include on stage, but nonetheless are important. So I want to close as we're coming to our final minutes here with a question for all of you. So I'm going to pose the question, but then I have a few observations I was going to make. This will also give you all a chance to figure out what you want to say in response to it. And we'll go Ben down here to Bijan in that order. And the question is, we've had an amazing first 5 years. Industry partners and industry academic collaborations have been critical in the success of HDSI in the first 5 years. What is your one wish for the next 5 years? That's the question, is what is your one wish in this space of industry academic? I mean, world peace and, generative AI is not killing all of us. Yes, we all agree on those, but what else might it be? And I do want to make sure, while you're all thinking about this, to call out Sophia Tran and Eric Mion, the absolutely amazing industry partners team that we have at HDSI. We're up here on the stage, but they are the ones who make all of this really happen. And we are incredibly lucky to have two such amazing people giving us not support, but leadership, behind the scenes leadership in how to make the Industry Partners Program work, and work so incredibly successfully. So Eric, Sophia, thank you for all that you do. Ben, one wish for the next 5 years?
Yeah, generative AI not killing us is within our purview, I feel like, but I don't know that we can solve it. It'll make us think we solved it at best. Anyway, I think getting more visibility of the value to other partners would be really nice. How do we build on what we've done as templates to help other companies say, ooh, that, sharing is scary, IP is scary. I see how this is really beneficial to the company in the short run, in the long run, for hiring, for innovation. And same in the flip, right? More professors saying, that's cool, I want to figure out how to get access to those data. I want to figure out how to see my research hit the world more. Can we take what we've done and really snowball it?
It would be fantastic to achieve. Rasmus?
Yeah, I'm thinking talent. At the end of the day, everything is about people. Having the right people for the right demands in this market. So making sure we are very well aligned in terms of how we educate our younger professionals and how it aligns with the industry. So close collaboration there, make sure that we develop the right talent.
Great. Okay.
I think more storytelling about successes, and I would love to see clusters of successes and working models associated to those emerge. And my biggest wish is that alumni, who I see in between the seats, they'll be part of our industry programs and the mentors and capstone projects. So our network of influence will grow from our alumni.
Bijan. Thanks. You know, as the saying goes, if you want peace, be ready for war. And you know, Pat Gelsinger was on the Senate floor asking for funding for semiconductors, without which you can't fly planes or drive tanks, or basically you'd be reduced to throwing rocks at enemies. So one of the senators kept pressing him, like, why should we give you any money? You're a big company. And you know, he kept going back and forth, and it was a 2-hour-long session. One of the other senators asked him, well, suppose we do give you money, and suppose you do onshore and bring all the fabs here. Who are you going to hire? Where are you going to get all the talent? Where's your commitment to partner with industry? And that's where the outline of collaboration, back to people. Where are you going to find these people that can help? And that's why there is a big emphasis in collaborating with multiple universities and trying to put some of that in place so you can have the talent to address not just theoretic problems, but real problems, real world problems.
Yeah, it's really striking how people is the thread that runs through all of this for a place that I think is sometimes viewed as just about the numbers. That's all data science is. I think it's really important that the stories, the narratives, the successes, and the failures, the things that don't work, that we're willing to talk openly about them, because that's the path forward to really, truly co-designed collaborations that can make a meaningful difference in the world. So Ben, Rasmus, Ilkay, Bijan, let me thank you so much for taking the time to talk today and for coming out to this amazing celebration of the anniversary of HDSI, as well as the inauguration of this fantastic building that we are getting to be in. So thank you. Please join me in thanking our panelists. And I will now hand off the microphone to our wonderful host and MC, Vineet Bafna.
All right, we will take a last break, but I encourage you to stay around because we have the ribbon cutting ceremony next. They're going to do a little bit of prep work here. So there are some beverages where the posters are set up, and maybe I can invite you to go over there and also look at the posters again. And then just final few words, I'd like to thank all the HDSI staff, especially Simeng, but also Jennifer and Kelly and Logan and Matt and many other people who I'm not naming right now for doing a great job with organizing. Thank you all very much.
And a big round of applause to Vineet Bafna for actually organizing this fantastic program. Thank you. Thank you for coming. I'm pretty sure this is the first one, but we'll have many more occasions in the coming months. Thank you.
Hello. I have never experienced so much silence so fast. But thank you, everybody. Thank you for being here. For those of you who don't know me, I'm Pradeep Khosla. I'm the Chancellor. And we are here to celebrate the 5th anniversary of Halıcıoğlu Data Science Institute. So please give the Institute and the founders a big hand. So it's amazing. I still remember the first conversation I had with Taner to think about what would the big impact be that he would want to make. And at some point we converged on data sciences being the future. And this is long before Berkeley had started Data Sciences Institute. This is long before anybody had started data sciences. And Taner, if you don't know his background, comes from large-scale computation, and data science was one of his passions. And he actually said, you know, this could be really significant and important. So we said, why not? So we figured out what it's going to take. And with a very significant $75 million naming gift, Taner said, now you're supposed to deliver to me what I really expect. And what he really expected was a first-class, top-notch institute in a great institution. The institution was already great. So it was obvious that we had to find somebody who could really deliver this, how should I say, aggressive vision that Taner and his family had. So of course, Rajesh was around here, just stepped down as chair of computer science. So Rajesh, thank you very much for taking on the challenge. So please give Rajesh a big hand, because so we are applauding accomplishments that I have not described as yet, but I'm glad you trust me. And you're applauding in advance. So let me explain some of the very significant accomplishments. In 5 years, this is the third cohort of undergraduates that are going to be graduating like literally 10 days from now. One of the largest majors at UC San Diego. It is not capped yet, but it could be capped. But we think it should not be capped, not yet, because it is a very, how should I say, favorite major of many, many students. Secondly, in 5 years, there are 3 graduate programs that were defined, and that started in fall of 2022. There will be an online program, a brand new building, an old building renovated to be brand new, but this looks like a brand new building, and data science is going to occupy this whole building very soon in the near future, because data sciences, the institute has been growing very significantly. And this growth does not happen automatically. This growth happens because clearly Rajesh is a visionary. He has put all of his time, all of his life and energy, blood and energy into this. So he's done a really good job. But this is also supported by the administration. Dr. Continetti, where are you, sir? There he is. Bob Continetti, our Senior Associate Vice Chancellor in the EVC's office, has played an important role. So this institute, starting with what is called an institute, became a department without being called a department. And at some point in the very near future, we are proposing that it become a school and combined with the San Diego Supercomputing Center. And I think it'll be the first school of its kind to have not only the computational part, the data sciences part, but also the infrastructure part co-located simultaneously in one school, and the infrastructure part being, it's not all supercomputing, but being primarily the supercomputers, right? So there's a lot of exciting things happening right here at UC San Diego. We are trying to do business in ways that most institutions and universities cannot do, because not everybody has a supercomputing center, and we do, and we have one of the best supercomputing centers in the country. So is Frank here? Frank, where are you, sir? Huh? Oh, he had to leave, so I don't have to say anything then. No, all right. If you see him, tell him I was thinking about him and his leadership of supercomputing, which literally placed San Diego, UC San Diego on the map more than 2 decades ago. So we have been a leader in this area. So I cannot say enough good things, but let me just say one last thing, which is, Taner, thank you very much for your vision. To your family, to your parents, Mr. and Mrs. Halıcıoğlu, thank you for letting Taner help us. And Ned and Tishna, thank you for being here, for celebrating this 5th anniversary. So we are looking forward to multiple such anniversaries. We are looking forward to great accomplishments coming out of Halıcıoğlu Data Sciences Institute. And we are looking forward to a great tenure of leadership of Rajesh. So thank you, Rajesh, one more time. And let me now hand this over to my colleague, our Executive Vice Chancellor, Dr. Simmons, please.
Thanks very much, Chancellor Khosla. It's really great to be here on this 5th anniversary of HDSI. When I arrived at the institution to become EVC, one of the first projects I got pulled into was creating HDSI. I didn't even know what the initials stood for when I had just walked in the door, and it was really a feverish year of emails and drafting governance documents and redrafting them, and just one of the most exciting things. And now here we are with just so many accomplishments, as the Chancellor was saying, just a huge undergraduate program, multiple graduate programs, our first online degree ever. And every week, Rajesh seems to be telling me about another school that he's going to work with to make some kind of a joint degree program or special degree program, which is great. It's exactly how I want everybody to be working across the institution. I think it's so impressive the way that Rajesh and the whole leadership team, I see also the associate directors, Ginny Desa and Dimitris Politis are here somewhere. I saw you there, okay, hiding over there. That the leadership team has done such a wonderful job of using the essentially cross-disciplinary nature of data science to pull people together from all over the institution and to unite disciplines from ethics to statistics to entrepreneurship, and to bring people together who have very diverse backgrounds in terms of what field they're from, where they personally come from, how they like to work, whether they're researchers, whether they're faculty, industry leaders, and students, and pull everything together to really make transformative impacts. I think there are so many firsts here at HDSI, and I'm just continually inspired by the collective commitment of everybody within HDSI to create a strong culture so that people know what they're trying to work on together. When you walk into an HDSI faculty meeting, everybody's sitting and talking to each other about exciting things they want to be doing. Some faculty meetings in other places you may walk in and everybody's just kind of staring at their phone. But here, they know each other, they like each other, they want to work together. And that culture, I think, is also part of the reason why HDSI is leading the way and getting really big grants and pulling in people from other parts of campus to create new centers and new initiatives that will go beyond the core of data science and pull in so many disciplines, which is why, as the Chancellor alluded to, they need every square inch of this building already, because they keep hiring like crazy because everyone wants to be part of this. So growth in numbers, growth in intellectual ambition and connectivity, this is what we need to do to serve the people of California, and HDSI is doing a tremendous job. So we're here to commemorate the next chapter, the opening of the new building, right on the 5-year mark, and we're all eager to see what is going to be next on the horizon, and I'm sure you're equally eager to see that, Taner. You helped start it off, you got it launched, and now you're part of driving it forward. So thank you, everybody. So thrilling to be here. And now I think it's time for us to hear from the director, Rajesh Gupta.
Thank you, E.V. Siemens. This sign is from the founding day of Halıcıoğlu Data Science Institute 5 years ago. It's a piece of foam, but it feels heavier today, much heavier. And I touched it in the morning because HDSI means something today. It meant something today 5 years ago also, but that was an ambition. Today, it is a community of nearly 1,400 people, maybe 1,500. Think about that. Over 500 alumni. They will carry Halıcıoğlu Data Science Institute on their resume for the rest of their life as their major accomplishment. And in their success will lie our identity. There are over 40 faculty members, 28 of them brand new to UC San Diego, 22 of them assistant professors, 11 of them jointly with other schools. As I speak to you, we have 3 offers pending jointly: physics, linguistics, and GPS policy. I don't know of any other organization academically that has had the concept of being a hub really embodied this way. And Elizabeth, one more degree program. We have a proposal that we'll be sending out for approval this summer is MD-MS. Only an hour ago, Eric Topol gave a fantastic keynote about how medicine is changing. And the doctors in their training come trained with that subject. It'll take 10 years before the effects are shown. But that's the legacy we're working on. For 5 years, there was only one goal I had, and that was to attract talent so that we can train the talent of tomorrow. Everything else was a means to an end, from furniture to building to office to space to everything else. But now, we are moving from people to place. And this sign will have a permanent place to put. We will not take our signs away from other buildings, especially San Diego Supercomputer Center. They have been such a phenomenal host for us that I could not imagine them doing what they did, moving people around so that they can keep accommodating our growth. Nobody does that. And that level of support is not only from SDSC, but also from Jacobs School of Engineering, where I have held, and I continue to hold my appointment. And for 5 years, I've been away from the department doing something else. And that could not have happened without the unwavering support from the leadership of computer science, the leadership of Jacobs School of Engineering, the faculty colleagues who also have to vote on my promotion, which they did. And so Soren, thank you. Soren Lerner is the chair of computer science. There are so many people I have to thank for. I took whole of 10 minutes in the morning, so I will not repeat that. But really, it has been phenomenal, especially working with the oversight committee, my boss, Bob Continetti, EVC Siemens, and Chancellor Kosler. They are tough taskmasters. And I was the foot soldier who got to see what strategic planning is about and how to think strategically. And with that gift came the even bigger gift, your confidence and trust. Believe me, that has meant word to me. And I've been supported by a phenomenal faculty council. When we have our faculty council meeting, the attendance is nearly 100%. I mean, who goes to faculty meeting for 100% of the time and stays there 100% of the time? And the staff, led by Jen and Kyle, is just amazing. And you can see that here with the logistics and so on. So without much ado, I thank you from the bottom of my heart. Any more thank you, I will start crying, which you don't want. But really, this has been a great run, and I'm just beginning. And I'm looking forward to what is ahead, whether it's the school, whether it's some other name, it doesn't matter. But it is all about one thing. It will always be about one thing. The primary product of University of California, San Diego, the people, the students, the talent. With that, I want to introduce and I want to invite Priyansi Shah, a master's student. Priyansi, we created a master's program. But before we created a master's program, we created a bachelor's program with one purpose, that the master's degree was not necessary in data science. If you did a bachelor's in data science, you knew as much as what a typical master's in data science would do. Then what are you doing with master's degree? Master's degree was designed so that the students get a glimpse of what it is to push the boundaries of knowledge or experience. which means sign up for a research, sign up for maybe PhD program. And in fact, a large number of our PhD program students, I think 6 of them last year, went from master's to PhD program. And that's the vision we wanted to put that in place. So Priyanshi is a first-year master's student, also working in Dr. Sankash Subramanian's lab, and I'll let her speak about what her experience has been. Please be frank, is my test. Thank you, Priyanshi.
Hi, everyone. My name is Priyanshi, and today, as I stand here before you all as a master's student in data science at HDSI, I am filled with gratitude and a sense of purpose. Reflecting on my journey, I had a pivotal moment in my life when I realized the desire to use data to make a positive impact on people's lives. It was my tenure during my work at the industry as a data scientist where this calling emerged, and within me, I had the urge to seek out a university which would equip me with knowledge, skills, and impact needed for my vision. UCSD is one of the top AI research institutes in the world, and this is how I came across the data science program being offered by HDSI. Among the many courses, some of which that really caught my attention was working towards responsible and trustworthy AI, like interpretable machine learning. It was one of the top and happiest moments of my life when I received an admit from UCSD. The opportunity to study at an institution was a blessing, which I will never forget in my life, and I will forever remain grateful. From there, UCSD has been so caring and so supportive, right from the processing of the documents to helping my needs in my housing residential areas, and even suggesting me what to bring and what not to. During my time here at HDSI, I have had the privilege of meeting extraordinary people who have played an instrumental role in shaping my experience. I have had the honor of meeting our visionary founders, our dedicated professors, our talented batchmates, the staff members, and the advisors. The campus is so lively in terms of going to events almost every day. I feel that the campus resources that HDSE provides, like library and computing resources, have helped me a lot in my learning. For example, when I needed some data which was difficult to access, I easily requested library for that. I have also had the chance to network with a lot of industry professionals and alumni to HDSI events, and from there, I had a lot of learning from their experiences. HDSI stands at the forefront of providing exceptional research, and I believe it is the best for anyone who wants to go into research or into the industry. The curriculum is both focused on research and where I get deeper insights for any particular topic of my choice, and I also had the hands-on project experiences from those topics. Personally, I got the opportunity to work under the guidance of Professor Sankash Subramanian, and I'm really, really grateful to him for the invaluable mentorship that has shaped me better in my research journey. Looking back, I can confidently say that my time at HDSI has been and continues to be life-changing. The knowledge, the skills, and the experiences that I've gained here have transformed me into a catalyst for a positive change. Today, as I stand here, I carry within me a profound belief that I am certain that I will create a huge impact on people's lives someday. Finally, I want to express my deepest gratitude to HDSI and UCSD faculty members, my fellow batchmates. Let us all continue to harness the power of data and build a future that is not only technologically advanced, but also socially responsible and inclusive. Thank you so much.
So thank you, Priyanshi. It's my pleasure to invite Chancellor Khosla, EVC Simmons, Priyanshi, and Taner. Taner, thank you very much once again for the ribbon cutting. We got a giant scissors here. So Okay.
Smile for photos on the count of 3.
All right. After this, thank you. We have, I think, some photo moment. That was that. We just did that. Sorry, I'm not used to instructions. So we have a reception that begins at 4:25 in the patio here. And thank you very much.